Hey there, guys, gals, and non-binary pals. Welcome to RustConf 2021. My name is Sage Griffin, and I'll be your host. If you haven't yet joined the conference Discord, check your email for an invitation. If you are in the Discord, you've already agreed to our code of conduct. If you need a reminder on what's inside of it, you can find a link in the announcements channel. If you have any doubts over whether something you're doing is making someone else uncomfortable, assume that you are and stop. If you see something happening that needs moderator attention, please ping @moderators or find us in the help channel and we'll take care of it. The most important channel for you to keep an eye on is announcements. This is where we'll be keeping you updated on any technical difficulties that might arise, but hopefully won't, as well as any important updates throughout the day. Also in the Discord, you'll find a hallway channel, where you can have any off-topic conversations that you might have had in the hallway at an in-person conference. You can also find various interest group-related channels, such as parents, gaming, and queer. But the majority of the conversation will happen in the audience channel. This is a space for you to chat with your fellow attendees about the talk we're all watching at that given moment. You'll see a Q&A category where you can find a channel to ask questions to each of our speakers. Most of our speakers will be online during the talks to answer any questions that you might have. Please keep any of the general chatter in audience and out of the Q&A channels. This is the second year that we've had RustConf online. While it's not yet safe for us to all get together in person, I'm so happy we have this event to help us feel a little bit more connected. If you want to post some selfies and help us all feel a little bit more together, check out PhotoWall. That's a lot of channels, and it might be overwhelming. This year we asked if we could, without stopping to ask if we should. If you need help finding things or help with anything else, come ask us in the help channel. Next, I want to give a huge shout out to all of our sponsors. RustConf is only possible, virtual or in person, because of the financial support of our sponsors. This year, that sponsorship allowed us to have unlimited scholarships and nearly free student tickets so as many people as possible could attend. Sponsoring an online conference like ours, where we don't sell attendee info and try to keep things fun, really means our sponsors do it because they love Rust and just want to be around all you wonderful people. In exchange for their support, we promise them some FaceTime with all you lovely people. Since they can't meet you at the booth, this year that comes in the form of short promo videos. And some of them are pretty funny. So, short version, RustConf has commercial breaks. We won't do that obnoxious thing where the commercials get louder, we promise, but they'll broadcast between sessions. Most of our sponsors are hiring, and many of our top sponsors have their own channels in the Discord. Pop in and talk to them if you're feeling so inclined, and thank them for their support. You'll hear more about our sponsors in a bit, but for now, let's get into our first talk. Please help me welcome Nico, who's giving our project update on behalf of the Lang team.
So, hello, my name is Nicholas Matsakis, and I am the co-lead of the language design team along with Josh Triplett. I'm also a member of the Rust compiler team. I'm working on Rust for a little while. I started at Mozilla Research, but I recently joined AWS in January of this year, and I'm going to be telling you about where I think Rust is and where I think we should be going. So, let's get started. So, 2021 was quite a year. We went from last year, a project that was primarily supported by one company, Mozilla, to a project that has its own foundation with, at current count, 6 platinum sponsors, including many of the biggest names in computing. So, it's not bad. But if that's not enough, many of those companies have formed teams employing people to work on Rust, the language. Right? Pretty cool. So we've got a lot more people being paid to work on Rust this year than ever before, and including myself. I'm one of those teams. And if that is not enough to convince you that 2021 is some kind of landmark year for Rust, what about this? Rust is under consideration for inclusion in the Linux kernel. So that's pretty cool. I mean, given all of that, I have to ask you, is this it? Did we, make it? Is that what happened here? Well, that's an interesting question. I think to answer it, we have to go back a little bit and say, what was the goal? What was the purpose of Rust when we started out? It wasn't just to get in the Linux kernel, although I'm not sure I thought that would ever happen. But it was something different. It was to take the power of C and C++, right, and put it in a package that has that great feeling of JavaScript, and Ruby, and Python, the easy-to-use feeling, and get the best of both worlds. Have our cake and eat it too, I used to say all the time. And you can kind of put that in this like graph form, right? I see these kind of graphs a lot. I think they're good. So you got C++ on the one side, really strong performance, but not always so easy to use. And then you've got on the other side JavaScript and Ruby and Python, which are really easy to use. You can ramp up really quickly and get people started, and there's lots of people who you can hire to work on your project. But the performance, while sometimes great, other times, especially in like critical code paths, isn't what you need. Right? So the premise of Rust is kind of, bam, there we are. Top right corner, all the performance, all the ease of use, all the power, all the time. And when things are going well, there are times I think we actually do achieve that, which is really cool. So recently saw a blog post that I think is a good example of this. It comes from Tenable. There's a link down there. And you see that they had a logging service, and they rewrote it from JavaScript into Rust, saw a 95% reduction in memory usage, 75% reduction in CPU usage, and maybe you're not so surprised because you're thinking, well, okay, sure, if you rewrite JavaScript into a language like C++ or Rust, it's going to get faster. But, not only that, they did it all in a single sprint in 2 weeks. That's pretty cool. And it works, right? So that's kind of what we're going for, that you should be able to get this high performance stuff that was always possible but took a lot of engineering and maintenance effort, and do it with the same skill set that you use to develop JavaScript and so forth. Right? So, well, that is what we're going for. This is kind of how it should feel. Right? I think there's some sentences that come to mind when I think about Rust. Like, we want it to be performant. You often hear people kind of say, wow, I wrote this Rust program and it ran really fast right out of the box. Well, at least if they remember to use cargo run release, they say that. Other times they might complain and then find out that indeed it does run fast. Or they might say that after they've been working in Rust for a while, they've kind of found this curious thing that they've noticed that once they it took a while sometimes to get things to compile, but once they do, they tend to work, and if there is a bug, of course there are bugs, but they're not usually a result of like surprising Rust semantics, but more like somewhere in your logic you made an error. And what that means in practical terms is you can take a big program, do a kind of ambitious refactoring, get it to compile, and then find that it works the first time. Or you could take some loop and run it in parallel, and be confident that the compiler is going to detect any places where you might be using the same data from 2 threads in incompatible ways. And so your code just works, right? And what all that adds up to, the performant, the reliable, is that Rust is really meant to be empowering, right? We're trying to take complex things that used to be hard to do and make them easy to do. And so you can still do them. And, we want to make kind of wizardry stuff possible. Like, you want to use that nifty kernel API that everyone's talking about, you can do it in Rust and you won't have to deal with 100 segfaults because it's wrapped up in a nice, safe interface. Do you want to run code on an embedded device with no operating system? Go for it. We've got a whole bunch of people in the embedded working group developing all kinds of cool abstractions to make that easy for you to do. Right? That's what Rust is all about. But it's not always like that, right? If what we're going for is the ease of use of JavaScript, performance of C++, we're not quite there. We're maybe more like here. We've got the great performance. I think that we nail with hands down. And sometimes things are really easy, right? You're on the right path, like in that Tenable blog post. But using Rust, especially early on, still means spending a lot of time fighting the borrow checker and learning the tricks of the trade, kind of how to work around what that error message means. Our error messages can be really great, but sometimes they're really confusing. or what the right solution is to that particular situation. And I think you just can't claim that on the whole, Rust is as easy to use as JavaScript, Ruby, or Python. It's just not true. And you can see that in the data. And so here's some results. These are survey results from 2019. I don't have ready access to a chart from 2020, the most recent survey, but I'm sure the results are comparable. And so we asked people how long it took until they felt productive using Rust, which is kind of related to ease of use, right? How long till they felt productive? And you can see in this chart that there's a good chunk of people who get productive pretty quickly. This is sort of the tenable case. Less than a month. That's great. And the only reason that's even possible, trust me, is all the hard work that we've put into the design of the language, of course, but also all the stuff around it. The error messages, the documentation, cargo, the crates. Like without all that work, this number would be a lot smaller, the number of people who get productive this quickly. Unfortunately, you can see that for a lot of people, getting productive in Rust is measured not in weeks, but in months. And there's a pretty decent chunk of people over here on the left that say they've never felt productive at all. Now, when I read that, I thought, well, I bet they're all beginners, right? I bet they're just using Rust for a week or two. Wrong. That's not quite right. So when I thought that, we cross-referenced the data with, well, how long have those people who don't feel productive been using Rust? And you can see that it's all over the map, right? Some of them, they've only been using it a few months. So yeah, they're kind of beginners. That's the largest chunk. But for some people, they've been using Rust more than 3 years and still don't feel productive. Right? Now, it's difficult to interpret survey data. That might not be the language. That might not mean they don't know how to use Rust. They might just mean like the libraries they need are not there, or the IDE tooling isn't up to what they expect. That's what one person told me. And that might be true. But at the same time, I think these numbers give pause, right? Give room for concern. If we want people to feel as productive in Rust as they do in Python, and I do, we've got to do better. The fact is, Rust really rocks once you learn it. But getting that done can be pretty difficult. So I recently heard this best phrase ever, which describes the situation. Rust is the language where you get the hangover first. It's perfect on so many levels. I mean, first, the obvious one, getting used to Rust, it takes time, right? And once you're past that hangover that you get up front, and you get kind of the drinking period that normally comes first, you get that then. Like you have a new pair of wings, right? You can build and maintain ambitious projects, and you start using it not just for ambitious ones. I hear a lot of people saying, at first I used Rust to write this powerful thing I'm doing at work, but then I had this old script that I wrote, and I needed to modify it, and it was kind of annoying, and I wanted a library, so I decided to just rewrite it in Rust. Then I could use cargo. The code's about the same length, but now it runs faster than it did before, and I'm able to come back and modify it again and again without having to be afraid. So this is exactly why that metaphor is awesome, because it goes the other way, right? Many other languages, or in practice, what often happens, right, is it feels really great at first. You're writing a lot of code, the code's running really easily, but then the hangover comes, and you realize that there's these subtle bugs that don't show up until after it's in production, or you have to go back and rework it, and you can't find all the places you have to make a change. So all things considered, I'd rather have the hangover first. I'd just like to see what we can do to make it a lot shorter, or maybe have no hangover at all. That would be even better. So I think this whole setup, is exactly why Rust keeps winning that most loved question on Stack Overflow. Is because what that question asks is, if you're using Rust, do you want to keep using it? And people who are using Rust, once they've kind of gotten past that hangover and they're into it, they're in that sweet period that comes later. So they do want to keep using Rust. But, that's a really cool number we love to cite, but if you look at the most popular one, what languages are used the most, Rust doesn't do nearly as well. Now, granted, we come into 5% of respondents, number 19, which is way better than I ever thought we were going to do when we started working on this project, right? But still, I think Rust deserves to be a lot higher in that list. I think there's a whole lot of projects that would benefit from being written in Rust. They would go faster, they would use less resources, and it'd be easier to maintain, and people would like it, but they're not doing that today. Right? So that comes back to my question. Are we there yet? No, we're not there yet, but we have come a long way, right? 2015, that's when we did our 1.0 release. That was basically the, hey, we showed Rust can work. What had seemed like a pie-in-the-sky research effort was being used to ship production systems. That was really cool. Now, 2021, we're showing Rust adoption has grown to the point where it is used in many critical systems that underlie the internet and in all kinds of places that you are almost certainly using today, right? And we're seeing more and more Rust developers getting hired to work on the project. I think we can expect that trend to continue. So we're getting out of this trap of kind of relatively few developers working on it, which I think is going to be great, and it's going to lead to more and more development and help us grow faster and sustainably. But if the next goal, is to achieve the widespread usage that I said I think Rust deserves, I don't think we're there yet. And I think there's space for us to grow, and there's a lot of places where we'd be a good fit if people could just learn it. So, how do we get there? How do we get Rust into widespread usage? Well, we do the Rust Evangelism Strike Force, because that works great. No. I think, going out and hectoring people into using Rust isn't probably going to do the trick. I think we need a different approach. So, what about this? What if we said a goal for ourselves? Instead of taking 6 months, which is a common number right here, for people to feel productive in Rust, what if we could make it so that they felt productive in 6 weeks? Or even less? Yeah, that would be pretty cool, right? I mean, I'm not sure how we're going to do it, but it would be pretty cool. Well, I think it would be more than that. I think it would be transformative, and I think we can do it, but we have to really up our game, right? We have to approach it very deliberately. And there's going to be a couple of things we have to do. So one of them, the two that I listed here to start, is we're going to have to be focused, and we're going to have to be really creative. So when I say focused, what I mean is we've got to keep our eye on the ball, on the goal of making Rust easier to use, shorter time to productivity, without sacrificing all the things that make Rust great, right? If we just end up turning Rust into another language, nobody wins. So I think the way we should approach this is we need to identify the ways that we want Rust to feel. I've given 3 here. There are some, I think there are more we can say, but we want Rust, for example, to be reliable. We want that if it compiles, it works. We want it to be performant. We want it to be empowering. And if we keep our eye on those goals, and when we're working on a design, we sort of make sure that it feels all those ways, then I think we're going to find we're doing better. And if it's not, that's where the creativity part comes in, right? We're trying to get a delicate balance of exposing a lot of complexity in a really simple way, and it's really hard, and we have to think hard, and we have to try a lot of different approaches before we actually are able to do it. So, we need to both be focused on what we need to do and be creative in the ways we go about doing it. Okay, so what else? Well, we need to think broadly, by which I mean we have to look at the experience of using Rust holistically. Look at all the things users are trying to do and figure out how to make sure that all the pieces they need to do those things are there, even though a lot of those things aren't going to be under our direct control. They're not the language proper or the standard library, right? So actually, we can give a good example if we go back to that blog post I started out with, the one from Tenable, where they reduced their resource usage. If you look at their blog, you're going to find that before that post came another post, one where they were evaluating Rust and deciding whether to use it. It's a nice read. It's called Building a Microservice with Rust. And one of the things that I liked about it was they went through what are all the pieces of the puzzle they need to build a typical microservice. Right? So here they have a clear goal. They're going to build this service, and they need an HTTP API, code to work with the database, code to read messages from the queue, a Docker file, and so on. Right? And you can see how they found most of those pieces, and some of them they had to kind of cobble together with some scripts and other stuff. And that gives you a clue. Well, maybe that's a missing piece, right? That's something that if you didn't know what to do, you might get stuck. And if we want to push productivity down to a few weeks, we need to make sure that all those pieces actually are there and are documented. And that includes like kind of glue code, or libraries like I just talked about, but also things like documentation, IDE integration, and debugging support. So learning ownership and borrowing, that's always going to take some time, but the rest of that stuff we can definitely solve. We should do so. All right, so we're going to think broadly. Now, what else are we going to do? Well, we need to be bold. We've got to be willing to take some risks. So if you want new results, and I do, you've got to do new things, right? Here's a list of things we've never done, mostly for good reasons, I will say. And I think, though, we're going to have to revisit and take a careful look at our hard lines and our fixed assumptions of things that we know are a bad idea, and try to reevaluate them in terms of those experiences. Are we really, is it really preserving the experience to have this fixed rule, or can we change the rule in a way that makes some other parts of the experience we want better without, say, hurting the performant part of the experience or the reliable part? And I don't know if these specific things, these specific questions are the right ones, right? I can't tell you exactly which assumptions we have to reevaluate, but I can tell you for sure that if we want to get the goal of being productive in 6 weeks, if we want to make Rust a kind of widespread mainstream language, and I do, we have to be willing to re-examine those basic assumptions and make sure that they still hold. So, on the topic of revisiting, re-examining basic assumptions, let me turn a little bit and talk about the Rust 2021 edition. You may have heard, we have one this year. Woohoo! Yes. And editions are really cool because they give us this awesome tool that lets us remake decisions that we made and tweak them if we think we might like to do it differently without breaking all the code that already exists. So, how does that work? The idea of an edition is simple. Every crate declares what Rust edition it's going to use. So Rust 2015, that's kind of the 1.0 release, Rust 2018, and soon to be Rust 2021. And no matter which edition you're using, your crate interoperates with all the other editions and all the other crates, right? Editions are an internal implementation decision. They don't affect your ABI, or they don't affect your ABI. They also don't affect your API, right? And even better, if you'd like to upgrade from an older edition to a newer one, we have tooling that will do it automatically for you. Right, so this is not a split the ecosystem situation. This is just get access to newer and better Rust. And what we use editions for is to make targeted improvements that make Rust easier to use. And it's often the kind of stuff that you probably wouldn't even realize it changed. It's just that there were corner cases that made it impossible for us to improve Rust in a way we wanted to unless we were willing to tweak the rules. So here's an example of something like that. Today in Rust, when you have closures, they always capture an entire local variable. So these two closures here, they will both capture the tuple variable, which means that they're going to get in an error because you can't have two owners of the same variable at one time. But in Rust 2021, this code actually works. And that's because the compiler observes that they're accessing different fields of the tuple. And so it'll give tuple.0 over to this first closure and tuple.1 over to the second closure, right? And now that's great. And once I saw this pattern, I started to realize how often, it comes up that I'm doing little workarounds for this limitation, and now those little workarounds won't be necessary. But making this change did require us to use an addition because it can affect when destructors run, when memory gets freed, other subtle things. So I want to just give a big shout out to the RSC 2229 project group for their hard work on this. They were really persistent and they saw it through, and it's going to be awesome. Now here's another example. This is not a subtle change that you'd never notice, but it's a pretty cool feature that doesn't really break much stuff and mostly just works, except for the occasional corner case, which is that we used to require you to put variables outside of the placeholder like this when printing, and soon, not yet, but we will allow you to just put them in line. This is actually going to work on all the editions. The problem that we had to use an addition for is that when, in certain cases of like panicking, accepted certain rather dubious things used to be accepted in work around panicking, and we had to change those semantics a little, and additions let us do that. So that's really great, and shout out to Mara for making that happen. It was an epic effort. And I don't have time to go through all this stuff in the edition, but let me just call out a bunch of people who contributed. You all are fantastic, and thank you so much. The edition's going to be awesome. So, all right, we're ready to be focused, creative, bold. What do? It happens that this very question was facing us earlier this year, as we thought about how to approach async Rust. So you may recall that in 2019, we shipped the async await MVP in Rust. This was a huge achievement. The design was really cool, and the implementation had gotten done, and we were ready. It had taken many years, but we were ready to see it come into practice. And in the time since, I think we've been validated for all the effort we put into it. There's more and more uses of async Rust. And we've had a lot of time to gain quite a lot of experience. And we now, it's time to look past that MVP and see, what do we really want async Rust to be? How can we make async Rust reliable, efficient, performant? What does the full feature look like? And the problem is, there's such a huge range of possibilities, right? And so many variations to explore, so many ways it could be. So how do we get everybody on the same page with what it should be? So I raised this question with Shane Miller, who works on the AWS Rust team, and she shared with me some of the approaches she had used to do similar drives within Amazon and elsewhere in the past. And I thought it was pretty cool. So the idea was, basically you start out with an in-depth examination of the status quo. What's it like to use async Rust today? And get detailed. And you find out what problems people want to solve today, what problems they are solving, and the challenges that they face in doing so. And these challenges are often not in the areas you think. It's a really simple example. When I discuss async Rust with working programmers, oftentimes the first thing that they talk about is, what IDE should I use? Or how well does the debugger work or not work? Right? How much raw assembly do I have to deal with when I'm debugging? That stuff is totally independent from async Rust, but it's still a blocker to adoption, right? It's what stops them from feeling productive, so it's totally relevant. Anyway, once you get a good handle on the status quo, you start to think about the shiny future. The idea is to go back through those status quo stories of what people were trying to do and what problems they hint, and reimagine, how could it be, right? And that brings you to, first you start out with what you want it to be like, and you go backward and think, what are the steps? If I had a feature that did something like this, I could have that happen. How could I get a feature that goes somewhere like that? Let me go backwards further until you have a path, right? Maybe a shaky and unreliable path, but a path that's going to take you into a really awesome experience. So we did this for async Rust, and we were trying to figure out how can we approach this in an open source way, right? So Tyler Mandry and I led the Async Foundation's working group, and what we did was we did this collaborative effort. So it wasn't just one person drafting it, but rather we went out and we consulted, keep my slide there. We consulted the community sort of pretty broadly for ideas about the status quo, about the shiny future. I mean, we ran sessions where we had people come in and join us with a HackMD, a shared HackMD, and we would write stories together that worked in all the experiences of the people in the call. Sometimes we went and talked to companies or in private conversations to get a feeling for how they were using it, for things that they made, in building their own software. So, and out of all that, we kind of developed this picture of what the shiny future and the status quo look like, right? And I want to talk to you a little bit about that. So we started out with some of the basic experiences, right, in terms of thinking about the shiny future, of how async Rust should feel in a year or two. And one thing is it should be consistent, right? You should be able to basically, if you know synchronous Rust, learning async Rust should be as simple as adding some async awaits and taking advantage of a bunch of new capabilities. The smaller we can keep the gap between them, the easier it'll be to move from one to the other. Now, in practice, what we found is that's not always true, right? So there has been a lot of effort to keep them analogous, but some things are more different than it seems like they should be. So take, for example, this is an iterator trait. This is not async. It's standard Rust, synchronous Rust. It requests the next item and takes ownership of it. And if you look at the async version that's currently in Nightly, you see it looks pretty different. It's got a different name, it's called stream, and its method isn't called next, it's called poll next, and it uses this thing called a pin, and what it does is it basically asks, is the next item ready? And if so, gets it, and otherwise says, no, it's not ready, right? Which is the underlying mechanism that you use to implement futures. So it's kind of exposing this abstraction up. If you want to implement this trait, you have to understand futures all the way down. Now, what we'd like to get to, and what we think we will get to, is this async iterator trait, which looks pretty much exactly like the synchronous iterator trait, except it has the keyword async. Right? Well, that fulfills our experience that we're looking for. And getting there is going to require implementing a bunch of interesting stuff, a bunch of which is already underway and has long been desired, like type alias, infiltrate, generic associated types. But the end result is going to be this really simple experience, which is great. And here's another example. This one has to do with looking beyond the boundaries of the language at all the things that people need for the full life cycle of what they're trying to do. So one thing we found when talking to people using Async Rust is that there's a real gap in tooling that emerges when you shift from synchronous to asynchronous Rust. With synchronous Rust, most of the things you're doing, like processes and threads, and they're well understood to the operating system. So you can use kind of C-based tooling, which has its flaws, but things like perf and so on, to analyze performance, and it works pretty well. But with Async Rust, the user space scheduler has a whole lot of concepts like tasks and channels that aren't understood by the runtime, and it's really hard to visualize them. And that makes it hard to debug problems. It also makes it hard to do things like get live metrics of your services that are in production, which a lot of people like to do. So fortunately, there's a lot of effort within the ecosystem itself to address this need, right? So Tokyo, for example, Eliza Wiseman is building this really cool thing called Tokyo Console. It's kind of giving you a top-like view of all your asynchronous tasks. And it's going to get extended in various ways. There's all kinds of plans to detect and warn about common pitfalls and replay events and so on. And so I think seeing developments like this is going to work to make using Async Rust from start to finish a productive, enjoyable experience. And another interesting thing about it, well, I'll get to that interesting thing in a second. So there's some more things in the Vision doc that I don't have time to go into. You should definitely check it out if you'd like to read it. So we've got, for example, APIs to go across runtimes and spawning tasks and so on. It's going to be a pretty cool feature. So that other thing I wanted to mention, it's kind of a general point. Whenever I talk about making Rust easier to use, I think a kind of warning flag goes off in people's minds that they think that this is going to come at the expense of the power and flexibility that they came to Rust for. And I think, as I said earlier, if we succeed in this goal by turning Rust into a different language that it no longer achieves the goals it set out to do, the great power of C++, if we fail, then we haven't hit that upper right corner that we're shooting for. And but what I found in practice is that this tension between easy to use and exposing power, it's very real, but it's also very surmountable. And when you do it, you get a kind of better for everyone feeling. And work that goes to benefit one group usually winds up benefiting all the groups if you do it right. But the console project is actually an interesting example of this because it started out as an effort to help people who already had services kind of going into production or who were debugging their really complex async Rust. So they already know async Rust and they need help debugging it, right? It's like a late stage feature. But what we found when we, well, I didn't do these demos, I shouldn't say we, but what I've heard from people who were doing demos is that just seeing the set of tasks help people to understand the model better. So it becomes also a teaching tool, right? It was targeting late stage, but it's useful for early stage. And definitely, I think anyone who enjoys the ease of use that Rust already offers knows that focusing on early stage also benefits late stage. All right. I would also point out, I guess, just that working on async itself benefits synchronous, right? It's another example. It's not about early and late, but about working on one area of Rust often requires fundamental work that improves and extends all of Rust. So what's next? I think if we can achieve these goals, and we will. What we're going to do is find that we aren't just making systems programming accessible to more people, which is what we've often talked about, but we're even changing kind of what systems programming is, in a sense, or what systems programming languages are used for, at least. Right? So instead of being the go-to language for critical systems, Rust is going to be the go-to language for anything running in the cloud, embedded devices, and all kinds of things, things where reliability counts. Right? And if we do that, what would that be like? It'd be pretty great. We've always found when we're going to have more people, that's going to bring us more good ideas, because people have good ideas. Having more good ideas is going to make Rust better, which is going to lead to more people, which is going to be a nice little virtuous cycle. Right? If we can get on that train, we're going to find Rust accelerating and improving faster and more than ever before. So thank you so much. This is the end of my talk. As I said, I'm really excited about what's coming up for Rust in the next few years. I hope I've gotten you excited, and I hope you enjoy the rest of RustConf. All right, ciao.
Next up, we have another project update. Please help me welcome Mara, giving a project update on behalf of the Libs team.
Hi, my name is Mara, and I'm going to tell you a story. A story about things getting stuck. A story about the standard library. About large changes and small changes. About 300 common GitHub threads and running out of energy. On how to move things forward when they're stuck. A story about focusing on one tiny thing at once. Chapter 1. Problems. Once upon a time, there was a standard library. And that standard library needed some synchronization primitives. Most important of all, the mutex. Its name stands for mutable exclusion, and a mutex is used to provide mutable exclusive access to something, usually some data or some other resource, such that it can be safely shared between threads. The idea is simple. You first have to lock it, and only then do you get mutable access to the thing it protects. When you're done, you unlock it, allowing others to lock it again. If you lock it while something else already holds the lock, your thread goes to sleep, and the lock method only returns once it actually exclusively locked it. So, a mutex is a way to share something between threads, allowing them to mutate it, while still upholding the fundamental guarantee that there's only ever one mutable reference to something at once. There are more synchronization primitives than the mutex, but those are not very important right now. What is important though, is that implementing these primitives yourself is hard. Bugs in lock implementations are often very subtle and very hard to find and debug. They are a complex interaction between very low level and sometimes even architecture specific code and the operating system. The operating system has to be involved because threads need to be put to sleep and woken up, and scheduling is the responsibility of the operating system. But luckily, operating systems already ship with an implementation of these. On Linux, Mac, and other Unixes, that's part of pthread, which is part of the POSIX standard. On Windows, they are called critical sections, or on newer versions of Windows, we have the improved SRW locks, or slim read-write locks. So, given that they're already implemented for us, can we just wrap them and be done with it? Unfortunately, the answer is no. These were designed for C, and they don't exactly match the requirements of Rust. There's many very subtle things you would do differently when designing an implementation for Rust, but I'll highlight just 3 of the bigger problems. First problem. In Rust, if you own an object, you can move it to a different place in memory, or at least when it's not borrowed. That means an object cannot assume it will stay at the same memory address over its entire lifetime. These lock implementations, however, do not allow their objects to be moved. Here is the documentation of SRW locks, for example, and it clearly states an SRW lock cannot be moved or copied. With most actual implementations today, moving would actually work perfectly fine, but their specification or documentation simply doesn't allow it. Future implementations might work differently, so we have to follow the specs. So, as a workaround, we allocate them on the heap. We put them in a box. That way, if you move the Rust mutex object, the actual underlying system mutex does not move. This works, but it is inefficient, because now there's allocations and indirections involved. And it means we cannot construct these objects at compile time. So you cannot just have a static mutex object, because it needs to be allocated at runtime. Second problem. In Rust, wrong usage must be safe. In Rust, we have this very well guarded border between safe and unsafe. there are plenty of things that are wrong or unwanted, but still perfectly safe in terms of memory safety. A program that always panics or loops forever is probably just plain wrong, but it is perfectly safe. Let's take a look at an example. We have a mutex protecting some integer, and we lock it. And then, sometime later, before unlocking it, we try locking it again on the same thread. This will result in a deadlock. It will wait forever until the first lock is released, which will never happen because we're stuck waiting. This program is definitely wrong, but it is safe. Deadlocking is safe. Unfortunately, the OS locks do not always guarantee a deadlock in this situation. If you relock a pthread mutex on the same thread, the behavior is undefined, or at least when using the default settings, which was a problem in older versions of the standard library. And critical sections on Windows are actually reentrant. That means they purposely do not deadlock when you relock them on the same thread. It will actually succeed. So if we go back to the example, we can take a look at what would happen if we would just wrap those mutexes in Rust. We lock a mutex and we try to lock it again on the same thread, but this time we do not get a deadlock. It might succeed. Then afterwards, we have locked the mutex twice. Both lock methods promised exclusive access, and now we have two mutable references to the same data. This breaks a fundamental guarantee of the Rust language, resulting in undefined behavior. And finally, a third problem. In Rust, leaking or forgetting things is safe by definition. Again, usually not something you want, but perfectly safe. An example. We have a mutex, we lock it, and then we forget that we locked it. It never gets unlocked again. The mutex stays locked forever. Later, the mutex gets dropped while it is still locked. This is safe because the compiler knows that we have no access to it anymore. The only thing it had is forgotten. These locks, however, may not be destroyed while locked. Here's a screenshot from the pthread documentation, and it clearly states, attempting to destroy a locked mutex results in undefined behavior. Conclusion. Rust is not C, and retrofitting Rust's concept of ownership and safety on top of existing things is hard in very subtle ways. Rust is fundamentally different. Trying to fit the C-shaped peg into a Rust-shaped hole doesn't always work. Making it actually fit requires force and frustrating workarounds. Chapter 2. A solution. On a Friday morning in September 2018, 3 years ago, Alex from the library team then brings up these problems on the internals forum. He also suggests a potential solution, replacing these locks by parking lot. Parking lot is an idea that originally comes from WebKit. The idea is that if you have a way to put threads to sleep and wake them up, or as they call it, park and unpark them, you don't need anything else from the operating system to implement your very own locks. The parking lot is a global data structure where threads go to sleep and wait, which keeps track of what they're actually waiting for. It is implemented using low-level operating system primitives, which vary a lot per platform. Once you have such a parking lot, you can implement your own minimal mutexes without having to think of the operating system at all. There's a Rust crate called Parking Lot, a very popular one made by Amanieu, which provides a Rust implementation of this idea. And not only does it implement such a parking lot, but most importantly, it implements mutexes and other primitives on top of it. Its mutexes are just a single byte and require no allocation or other runtime initialization. That means they can be constructed at compile time, so you can have them as static variables too. That locking and forgetting is well defined, and there's no way to cause undefined behavior with them if you stick to the safe interface. So this seems like the solution to basically everything we talked about. There was a bit of discussion, but people are positive. And not much later, on a cold and rainy Saturday morning at the start of December, Linus Fernstrand opens a pull request. A pull request embedding the entire parking lot crate into the standard library and changing the standard library to use it for its synchronization primitives. Quickly afterwards, several people began to review the code, discussing potential issues. More and more comments were posted, which were all quickly addressed. But this continued into the new year in January, and discussions went well into February. And then March, and more in April, and still in May. And even in June and July, discussions were still going on. And if you scroll a bit further, you see November popping up. So, what's going on? What's blocking this? One of the problems was simply that it is a huge amount of new code, or at least new to the standard library. Not only is it a lot, but it is also the kind of code that requires very specific knowledge of atomics and all kind of operating system details. There's very few people who know all these details of the operating system, let alone of all operating systems. An example, on Linux, parking lot uses a syscall named futex. It's a very low level function that is also used by pthread implementations to implement their mutexes. The standard library had never used this syscall before, and some questions came up about whether it's okay to start using it. Which versions of Linux support it? Is it maintainable? Is it easy enough to understand? This wasn't really a big blocker, but it was yet another topic on top of the already large amount of things to discuss. On older versions of Windows, where the necessary functionality wasn't available, it used something called NT-keyed events, which are undocumented. It is not as bad as it sounds, because they're still well known and only used on versions of Windows that do not change anymore, but it was just yet another discussion to have. And then there were the stability guarantees. Switching to parking lot would mostly be just an implementation detail. But there were some very subtle things that would be publicly visible and might be considered a breaking change. These were probably not a big deal, but yet another thing that needed to be discussed and needed a decision. I could go on with this list. I'm not even sure if I know the full list, but the overall issue is clear. There were just too many things to be discussed at once. The author and other people had tirelessly worked on addressing all the comments and issues, and a lot of progress was made. But after all this time, activity on the thread was rapidly slowing down. By the time yet another year had started, there were just a few more comments, until eventually everyone just ran out of energy. The momentum was gone, the PR was closed without getting merged, leaving behind a massive discussion log of almost 300 comments. So, what is our conclusion here? It's sad and frustrating when a large change ends up like this, but it's very normal and it happens all the time. Things are always harder than they seem, and the only way to move forward is to just try it and see how it goes. So I guess what I want to say is, large changes push things forward, even when they fail. Even though this pull request was not merged, it had a big impact. Things in parking lot had been improved because of it, and we now know a lot more about what needs to happen to improve the standard library's logs. So a next attempt should be much easier now. This brings us to chapter 3, stuck. We're now in the year 2020, and at this point, we are in an interesting situation. What's happening now is a weird kind of deadlock in the progress towards better mutexes. A kind of deadlock that happens surprisingly often in the Rust project, and I bet in many other projects as well. What's happening now is that every time that someone brings up some small problem or some improvement to the current logs, people reply with, "Oh, but parking lot is going to solve this." It makes changes to the existing logs very low priority because people are still expecting parking lot integration to happen sometime soon. People are hopeful. But at the same time, if someone then asks, what's happening with parking lots? When is it going to be integrated and what needs to happen? Everyone just gets silent and points at the massive discussion thread from before. There's no good overview of what the problems were. There's no list of changes that need to be done. There's no clear place where to start. And just like that, a failed attempt becomes an obstacle. While a previous attempt with meaningful discussion should have made next attempts easier, it also, somewhat surprisingly, can make it much harder to start on a new attempt. Someone working on a new solution would first have to overcome this obstacle. They have to read through years of discussion to know if their attempt is making mistakes that have been made before, and in which ways their attempt is different. This takes a huge amount of time and energy, often more than someone is willing to spend on it. So we now have, on one hand, people who are assuming that this parking lot integration is still going to happen soon, and that results in small things getting blocked or shut down. And on the other hand, we have new attempts at parking lot integration that are just not happening. And over time, we have less and less context of what it actually got stuck on. If you ask 5 different people of what this change got stuck on, you'll probably get 5 different answers, because no one really remembers all the context anymore. The conclusion here is not that anyone did anything wrong here. We just need to find better ways to recognize situations like this, and then find a way to handle them. As for recognizing this, I hope this talk will help a bit. For handling them, that's a lot harder, but I have some ideas. Let's start small. Chapter 4, Tiny Steps. Instead of trying to gather all the context and reconstruct the entire web of all the different issues that were involved, you can take a look at one single obstacle at a time. Pick the tiniest obstacle you can find and try to move it out of the way. Try to find a way to fix it in a way that does not touch any other parts. I'm going to quickly talk you through a few examples of small obstacles I tried to get out of the way. A few small changes, which I hope will make a future attempt at a large change in this area more likely to succeed. Obstacle 1. Stability guarantees. The standard library documentation makes a lot of promises which we usually never try to break. That's part of our stability guarantee. There's one small promise about mutexes, however, that we would not be able to keep if we switch to a more efficient implementation, whether that's parking lot or something else. I'm not going into much detail now, but we basically promise to panic in certain situations. With newer mutex implementations, we can no longer always give that panic in those situations. It's not a big deal, because instead of panicking, it will just work, and it's very unlikely that someone actually relied on this panic happening. In fact, when it was brought up during the original big parking lot integration PR, the reviewers seemed fine with this change. But it will be something that will be brought up next time. Digging up the old discussion then would help, but it will still be a distraction. So I sent a very simple pull request that just removed that specific detail of the promise. I described the context, and the entire team signed off on it. agreeing that this change is fine, after which it was merged. So, obstacle 1, gone. One fewer distraction, next time it would have come up. Obstacle 2, movable mutexes. Because these system mutexes we use are not movable, we put them in a box, on the heap. New implementations, such as parking lot, no longer require that, which is great. But we didn't have a mechanism for keeping the box on some platforms and removing it on others. That would become relevant if we don't want to or cannot switch to a new mutex implementation on all platforms at once. So I worked on making it possible to make this decision for each platform individually, to make it possible for potential future improvements to be made per platform, allowing for smaller changes. To have a reason to do so, I looked for a first platform to unbox the mutexes on, to no longer put them on the heap. Unix platforms were out of the question. POSIX doesn't allow it, and there are many different implementations that all need to work with Rust. On Windows, it's also not allowed to move them. The documentation is very clear about that. But then I found out Microsoft's documentation is actually on GitHub. And more importantly, it accepts pull requests. So I just sent a pull request, adding the promise that we need. Basically just adding a note, a clarification, that if the lock isn't borrowed, you can move it. And to my surprise, just a few days later, it was actually reviewed and merged. And now it's part of the official documentation. I'm not entirely sure what I expected, but I did not think it was going to be this easy. Anyway, now we actually suddenly have a platform, a very big one, with movable mutexes. So then I went back to the Rust repository and added a mechanism to allow unboxing mutexes on Windows, while leaving other platforms untouched. I have not been able to benchmark it, as I don't have a Windows computer to test it on, but I'm assuming it made a noticeable difference to the speed of the Rust mutexes on Windows, at least in the very contented cases. Anyway, now that it's merged, that means that next time we want to unbox the mutex on another platform, it's just a flip of a switch. So, obstacle 2, removed. Obstacle 3, new operating system primitives. Many efficient mutex implementations, such as parking lot, use a very low level of functions on the operating system. Specifically, on Linux, one would use the footex syscall, and on Windows, one would use the wait on address function. Neither of these had been used in the standard library before. A point of discussion that came up in the parking lot pull request is whether we are okay with using them, because we have no experience with them yet. So I figured, if we can just use these APIs in another place in the standard library, in a more isolated, simple case, we can get this obstacle out of the way. Since they're so useful for thread parking, I figured we can just implement the standard library's park and unpark functions with it. These functions are not used much, and they're more primitive than what a parking lot provides, but they are there and pretty simple to implement with these OS primitives without touching any other code. So I sent 2 pull requests. One to implement them using footexes on Linux, and another one to implement them using wait on address on Windows. The first one was quickly merged. The second one took quite a bit longer and had quite some discussion. Discussion that would have otherwise happened on whatever other pull request would have introduced this API. It was stuck for almost 2 months. 2 months that a future attempt at improving mutexes would have gotten blocked on otherwise. But eventually, this one got merged as well. So yet another obstacle, gone. Conclusion. Smaller chunks are easier to chew. I am not saying that everything can be easily split up in smaller chunks. Not at all. You can't just take a big complicated thing and cut it into some arbitrary small pieces and hope it works. But if you do see a way to break things up, it can really help focusing discussions and can really make it easier to make decisions by just focusing on one thing at a time. It does not solve any complicated problems, but it does make it easier to focus. Because then the smaller issues are no longer distracting from the bigger issues. Chapter 5. Moving forward. After contributing for a while, I was invited to become a reviewer and then later team member of the library team. At that point, I started to think more about what can be done, less in terms of code and more in terms of process and organization. Other teams had successfully been doing something called MCPs, Major Change Proposals, a lightweight way for someone to get feedback on something big they want to do before doing it. Big changes to the implementation of parts of the standard library could really use this too. However, the library team was mainly focused on the public interface and its stability. The implementation of the library had been the responsibility of the compiler team for a while, although they also didn't have much bandwidth for it. They would handle critical issues, but wouldn't have time for guiding larger changes. At that point, we decided to rename the library team to the library API team to highlight that their main responsibility is the public API. And that's when I created a new library team to focus on everything else library related. So now we actually do have a team to handle library MCPs and more. And now the API team can guard stability and work on API design without getting distracted by implementation details. We're still figuring out the best way to do things and what our responsibilities should be, but so far things are going pretty okay. Far more important than the teams, though, are the contributors. Teams just exist to facilitate, to guide, to make decisions when necessary, but most of the work is done by the contributors. Our main task is making sure that those contributors can, well, contribute with as few obstacles as possible. There are many things that are far from perfect. Contributing can be a frustrating experience. We often have to say no to things, but we should be careful to not scare contributors away. We should guide them towards things that we can actually say yes to. We should recognize if things can be split into smaller parts. And we should try to clean up after failed attempts, make sure that context does not get lost over time. We should recognize when something is blocked on something and figure out how to unblock it. This is all easier said than done, especially considering most of us are doing this in our free time, and we all have limited bandwidth and energy. But as long as we just keep making steps, small steps forward in the right direction, then we can achieve anything, eventually. Thank you for watching my talk, and enjoy the rest of RustConf.
Hey folks, this is Anatoly. I am co-founder and CEO of Solana Labs. We're really proud to be a sponsor of RustConf. It's been an amazing tool that helped us build a high-performance, low-latency blockchain over the last 3.5 years. None of us really were Rust devs before we started, and without Rust, I don't think we would have gotten here because of the high performance and the safety that the compiler provides. It's just been kind of the, our secret weapon when building applications. So we want to thank this community and we want to see it grow. And if you're a Rust dev that is interested in building high performance systems, software, or building financial applications or experimenting with blockchain, please check out Solana.com. So you should find job postings from us or from our ecosystem projects that are building smart contract applications. Or in the hackathon, teams are forming right now. So if you want to just see what it's like and participate and see if you can win a prize, just jump right in. We have a really friendly community. Everyone loves Rust, and we'd love to be a bigger part of the Rust community in general. So thank you so much.
Informal Systems is a cooperatively owned organization with employees around the globe. We're on a mission to build verifiable distributed systems and organizations that support sustainable growth. We specialize in the security of interoperable, fault-tolerant networks. These networks secure many billions of dollars in real-world value, yet they remain complex and error-prone. We aspire for people to be able to trust the systems they build and rely on. We care a lot about safety. We believe that verifiable and trustworthy relationships between people and protocols can flourish with the right tools and systems in place. Security and verifiability is core to the work we do. We're building critical infrastructure in the Cosmos network, like Tendermint and the Inter-Blockchain Communication Protocol, that serve as the foundation for new kinds of local economic systems. We're hiring to bring our vision of sustainable local organizations to the world. So if you're interested in formal verification, distributed systems, or blockchain technology, we would love to meet you. You can check us out online and contribute at github.com/informalsystems.
RustConf couldn't happen without the support of our sponsors. Before our next talk, I want to take a moment to give a huge shout out to some of our diamond tier sponsors. Huge thank you to the Rust Foundation, Huawei, AWS, 1Password, and Microsoft. Thank you for your support. RustConf couldn't happen without you. Now, without further ado, please help me welcome our next speaker, Miguel.
Hi, my name is Miguel. Today I'm going to show how move constructors, a technique from C++, can be used to express a new class of types in Rust. This type of programming has frequently been cited as being incompatible with Rust's object model. I'm actually going to show that we can make it work. To get there, we're going to go on a journey through Rust, to C++, and then back to Rust again. This talk is a bit dense, so please make sure to ask questions in the chat if you get confused. I'm going to assume an intermediate to advanced level of familiarity with Rust throughout the talk. To understand why we care about move constructors, we need to understand self-referential types. We want to create a type that can point into itself. We'll start with a struct that contains a value x and a reference to x, which we're going to call putter to x. Very creative. If we write this code, Rust actually complains, because Rust requires us to give explicit lifetimes to any reference inside of a struct. Now, we don't actually want to add a lifetime to the struct itself. We want a lifetime that is sort of like a self-struct that refers to the lifetime of the struct that contains it. Unfortunately, Rust really doesn't have a way of expressing this, so we wind up having to use a raw pointer. The barrel checker just doesn't know how to deal with this today. I'm going to be using these little boxes containing fields and addresses in order to describe what pointers are doing at any given time. They'll become very important once we start tracking self-pointers into different structs. Now that we're using raw pointers, we can make cycle self-referential after constructing it on the stack by, assigning putter to x to a reference to cycle.x. This creates a little cycle inside of the pointer. So pay close attention to these arrows because they're going to change over time as we do different things with the struct. We can implement a get function that uses the self pointer to access the other field. Although a little bit contrived, this is a real thing in certain data structures. Being able to create self-pointers is very useful for some classes of optimization and is pretty common in, performance-sensitive code. In order to get to work, we need to maintain an invariant in cycle. Putter to x must always be null, such as around initialization, or a pointer into itself and no other cycle. In other words, these are the only two shapes for cycle that are allowed. In particular, we cannot have a cycle that points into another. This is not allowed and actually breaks assumptions that we want to make about this type. Now, it's pretty natural to want to factor out this initialization code into a constructor function. The only change from the previous code is that we've copied the letmut cycle part into a function and then called that function instead of using the cycle that we initialized previously. But if we do, Rust will move cycle as it returns out of cycle new. When we return by value, Rust is a move which changes the address of the returned value. But because putter to x is unchanged, it points into cycle new stack, It no longer points to X. Not only does this violate our invariant, but it makes get violate memory safety, because reading data from destroyed stack frame is not allowed. This is pretty bad, so it means that we can't write cycle new this way while maintaining the other properties we want. Because Rust moves are implemented as bitewise copies, cycle doesn't get a chance to fix up its invariant. This is a general problem with self-referential types. Their invariants break if Rust moves them, and Rust really likes to silently move things. However, Rust does provide a good way to avoid this pitfall. Pinned pointers. PinP wraps up a pointer type so that unsafe code, like our get function, can assume it never moves. Moreover, it stops safe code from accidentally moving its pointee. Safe code can still do whatever it wants without hurting unsafe assumptions. In general, this means that you can't get a mutable reference into the thing behind the pinned pointer. You can only get immutable references because you can't swap or replace out of those. Most Rust types are unpinned, meaning that they nonetheless can get moved out of a pin. Like, you can unpin an integer, because integers don't really know about their address. But a self-referential type like cycle is sensitive to its address, and therefore can't be unpin. You actually usually disable unpin by adding a special type that I'll show later. Most importantly, pin isn't magic. It's a library type, and it doesn't really change Rust's core semantics. You can still move things around as long as you have them by value. This is unlike types like slices and raw pointers, which introduce entirely new language semantics. This will be important later because we will add additional library guarantees that don't change Rust semantics at all. So let's go back to our dangerous implementation of cycle new, because due to this move, it immediately invalidates the raw pointer we create. If we use pin, we avoid this entirely. By returning a pinned box, we ensure that we can't move out of it at any time. It certainly doesn't move when we return out of it. We also need to make sure that it's pinned. The phantom pinned type is a zero-size type that just disables unpin. Every type that cares about its address needs to include this type as a field. We can now write our code as before without any issues. Cycle.get will not dereference a dangling pointer. Note that we can't pull out of it like we could with a normal box. This ensures that safe code can't do anything rude. Pin lets us write unsafe code that requires certain values never move. There are a number of reasons you might want to do this. This comes up most commonly when writing asynchronous code in Rust, but there are other situations in which it's useful for, advanced data structures. It also enforces this in safe code. This means that safe code can't accidentally move stuff or do things that unsafe code doesn't expect. So unsafe code can do whatever it wants, and safe code can do whatever it wants, and unsafe code doesn't need to care. If you're watching closely, though, I actually needed to add a box to cycle new to allow me to return the pinned data. This is a problem. We need a pointer to pin in the first place. You can't pin an object and return it. That doesn't mean anything in the pin formalism. This leads to two major problems with pin. Number one, because stack pin data is going to be behind a mutable reference, you can't return it. It's the same as with any reference. Therefore, you need to pay the cost of an allocation and box it. We also can't pin data in collections. This is because basically every collection that can resize is going to move things when resizing. When a vec fills up, it copies everything and treats it as a move. When a hash map hits its capacity, it needs to do the same thing. Address-sensitive types don't really fit into the language, and using them widely is not free. Okay, so that's enough about languages that suck. Let's talk about C++. And no, this is not a C++ talk. I don't assume people have encountered it before, and I'm going to be very light on the weird C++ syntax. You can mostly treat it as Rust with a weird, different syntax and no borrow checker. Let's recall our cycle invariant first. Remember that when we have a cycle, we want it to be null or a self-reference. We cannot have this version where it points to something else. Let's implement cycle in C++. First, let's define fields like we did in Rust. Next, we're going to need to be able to construct it. In C++, you use constructors to create values. Unlike a Rust constructor function that might be named new, C++ constructors get access to this, which is the C++ equivalent of self. It is as if cycle new somehow took a self parameter. We can take the address of this in the constructor, which we could not do in Rust. When we call the constructor, it silently passes the destination of the new object as the this pointer. So, as you can see, the version in the constructor, which didn't really know the concrete address, gets a concrete address when actually constructed. To make this work, C++ allocates space before calling the constructor. So this alloc byte array is just random untyped data. We then use the special new syntax, which is kind of like a raw constructor, to tell it, hey, please run this constructor with this explicit this pointer. Finally, we cast it to the correct type, and it's just business as usual as before. You can call functions on cycle, and it's perfectly normal value. In C++, all values get constructed in place. That is, space is allocated before the constructor runs. As a result, C++ values are always implicitly pinned. They always know their address. They're all address sensitive unless you say otherwise. So what would this raw constructor operator look like in Rust? On the left side, I have desugared the C++ constructors from before. On the right side, I have a transliteration of that into Rust. The raw constructor will be some kind of function call that accepts uninitialized data and constructs an object there, which is the same signature as the raw constructor. Although the raw constructor does take an additional argument, and we'll see how that mixes in later. Naturally, we want to capture this function signature into a trait, new. New is a constructor object that can create values of a specific type. But remember that we want to leverage the fact that constructors create pinned values, so we need to make sure to mark the Rust version of this as pinned. To implement a value, to implement a constructor, we create a new type. New cycle is a constructor for cycle. It takes an integer argument and sets up the invariant, like the C++ constructor. The difference between this and C++ constructors is that the additional type captures the constructor arguments. So instead of taking an integer, the new takes self, and self contains that integer argument. For other constructors, you might have more or less arguments. Note that it is not cycle that implements new, because there are many ways to construct a value. For example, you could imagine a default cycle type that takes no arguments. Notice that the body of the Rust constructor is almost word for word identical to the C++ version. New lets us capture the destination address and store it just like C++. We can now set up the cycle invariant without transiting through the null state. Again, just like in C++. It's almost as if we've ported the feature all bugs and all. The new trait represents constructor objects. You can build a constructor with some parameters and then run it on some storage somewhere. New is Rust's equivalent of the raw constructor syntax, and is intended to be wrapped in a more ergonomic API, much like how you usually don't need to call it in C++, and you can use the syntax sugar of declaring a variable instead. Even though we can now create cycles without an intermediate null cycle, we still haven't actually solved either of the problems we had. Now that cycle is pinned on construction, we can't return them at all. Maybe that's better, or maybe there's an abstraction we're missing. When a function returns, it needs a place to put the return value, and this is some place in memory called the return slot. C++ constructors actually get special treatment in the C++ version of this. When you return a C++ constructor, it's not as though you're assigning it to a variable and returning it. What actually happens is it constructs it in place in the return slot. This means that this code, which wouldn't work at all in Rust, works perfectly in C++ and dodges the move on return hazard. C++ implements this by adding a hidden out parameter to every function, the return slot. The this pointer used for the constructor is the return slot, unlike a local variable like it would be in Rust, or at least that's sort of how Rust behaves. That said, Rust does have a return slot, and it does use it a little bit in the C++ way, but it's not in a way that is accessible to users, and certainly not in a way that we can use it to run a constructor. So what if we just ignore the Rust return slot and build our own? Wouldn't that be better? That way we can control how things get placed into it. Let's represent the return slot with, sort of reference type. That is data somewhere. It's uninitialized. We own it, and we're responsible for initializing it. It doesn't really matter where it is, but usually it'll be on a caller stack. Slots are the ideal location for running a constructor. They're raw memory waiting for a value to appear. We can define a method that accepts a constructor, runs it, and returns a reference to the result, consuming the slot. So in place takes a slot from the uninitialized state, uses a constructor, and then takes the initialized state that the constructor results in. We can then fake a return slot by passing in a slot argument. Instead of returning by value, we run a constructor in the slot and return the resulting reference. This is actually very similar to the C++ arrangement under the hood, and while still leveraging the borrow checker. Both the slot and the pin share the same lifetime, so you don't have any of the concerns you would have in C++ where the slot might not outlive the result. Okay, so constructors plus slots actually gets us the first of these. We can genuinely return objects on the stack, even if it's not quite as ergonomic as it is for unpinned types. Progress. We still can't do the collections version of this, but C++ seems to make it work, even though all of its pointers are pinned. So how do they do it? Let's look at our C++ cycle type again. When we assign a variable to another, C++ actually makes a copy, rather than a move like in Rust. Much like clone, by default, this is a bitewise copy, which means we can run into the same problem where the self-pointer invariant is broken. Oops. In particular, remember, the bitewise copy means the pointer does not get updated. But like Rust, we can actually customize this copying behavior. The key difference is that while clone in Rust simply returns by value, C++ copies are done with a constructor. This gives us a chance to fix up the pointer to the new location before it's available for potential misuse. So the copy constructor looks almost identical to the normal constructor. It sets up the invariant, and copies the data, copies X, but not the pointer. C++ variables don't move around like in Rust. You always construct new ones whenever you give a variable a new name. However, objects are always notified of when this happens, so you can fix up any invariants a bitewise copy would otherwise break. This is similar to clone, but it has all of the power of constructors. Obviously, we need to port this to Rust because it's really cool. Again, let's write down the C++ code and see how we might write it in Rust. On the left side, we have a copy. On the right side, we have the Rust constructors exploded out into the version that manually calls the raw constructor operation. Unlike constructors, there's only one copy constructor for each type, so it makes sense to give it a specific trait, which we're going to call clone new. We don't need to add an additional type that represents the cloning operation. It's like intrinsic to the type being copied. The clone new trait looks almost exactly like clone, except that instead of returning by value, it takes a destination parameter, just like a constructor would. Implementing it is super easy. Like, we already know how to implement it in C++. We implement it exactly the same way in Rust. It's the same with the other constructor. Now, we implement this on clone because, as I mentioned before, being copy constructible is a property of the type, rather than them being very many distinct methods for doing so. In C++, you only really get one copy constructor, so it doesn't really make sense to try to generalize it in Rust. The new trait is a fusion of clone and new. It's the cloning constructor. But in Rust, we really like to avoid having to make copies because move semantics are awesome. So how can we recover them? Let's recall back to our move slot abstraction. When we create a value in a slot, because the slot is a unique reference to some memory somewhere, we're actually the sole owners. No one else will ever access the value even after the slot disappears. We can introduce a new type, moveRef, which is like a mutable reference that captures this ownership property. Not all mutable references can be moveRefs because some of those might be outlived by other mutable references or other types that are entitled to run the destructor. moveRef has to be entitled to run the destructor. That's what ownership means. We can use moveRef instead of mutable references for the return value of in place, since it produces a brand new value no one else will ever access. The key point is that moveRef owns its pointee and not its storage. This means that we can move out of it, like box, but it's storage agnostic like a mutable reference. You can have moveRefs that point to the stack or the heap. Now let's recall copy constructors. They're like a constructor, but instead of accepting some special constructor type, they accept a reference to self and write a copy of the supplied destination. We can define move constructors analogously by replacing the source with a pinned moveRef. Pinned because that's what in place means. Unlike clone new, move new consumes the source, and that's why it takes a moveRef. However, the implementation is almost identical, and it reveals the true nature of custom moves. They're just copies that consume the source. However, they can also mutate the source to disable its constructor or, properly move an owned resource. This is exactly what Rust's move semantics do. For vanilla types, that is, unpinned types, clone new and move new are just the usual clones and moves. There's nothing special about them, and it shows that this concept actually reduces to something we've already encountered in Rust. Move constructible types let us move the immovable. Despite being pinned, we can move data from one location to the other. This doesn't violate the pinning invariance because we control exactly how the value is moved, in a way that unsafe code can be made aware of. The trait is generic, so we can build custom collections that leverage it. Instead of doing a bitewise copy to resize a vector, we can call the move constructor on each and every element as we're resizing it. This is how C++ collections, for example, resize when the contained value is not trivially copyable. Pin data in collection, so long as it can be move constructed, is totally something we can do. So yeah, we can actually do these things. We can make address-sensitive types feel as flexible as normal Rust types. We can return them, we can put them in collections, we can really allocate them wherever we want, and we can specify complex moving strategies that the normal Rust object model would not let us. That said, we need to muck around with uninitialized data in order to use any of this, and the ergonomics are really bad. Most people are not going to be writing unsafe code. They're going to be using these types and the unsafe code under the hood, but it would be best if they don't have to do any of that manually. So, emplacing a constructor actually only really cares about the constructor value you use. Everything around it is boilerplate that can be inferred. However, recall, returning pinned data is impossible, so we can't use a function to do this, but we can use macros to work around it. For example, the slot macro could be used to allocate some space on the stack and then immediately stick it into a slot so that it can only be accessed through the slot. Unfortunately, the slot macro can't even be an expression since it needs to allocate on the stack. We can use the emplace operation defined on slots previously to construct values. Unlike the example above, this produces a move ref. We can add convenience functions to slot that make it easy to call the clone and move constructors as well. So now we don't need to deal with any unsafe code in order to call constructors. We can just call this macro, allocate some space, and then put it directly inside them. This is a common enough pattern that we can add a macro to do this even more concisely. The choice of syntax isn't really important. Ultimately, we can make constructors feel simpler and easier to use. We could also potentially add functions that let us emplace macros into boxes, into arcs, and other similar things that you would want to do with a regular value. Really, it's a matter of what conveniences you want to add. Although constructors are implemented purely as a library, we can use macros to add custom syntax to use them safely. Ultimately, what they look like is up to the constructor library. This only scratches the surface of how macros can make constructors feel more natural and part of the language. There is still a lot to do in this topic. I already implemented the core traits in a crate. Check out move it on crates.io. I want to actually build a move-respecting vec and hash map like I described earlier. C++ has already implemented such things, so it's just a matter of porting the analogous thing from a C++ standard library. I'm most of the way there with vec. I don't know to what degree I want to attempt hash map until someone really needs it, because hash maps are pretty complicated. This concept is also very useful for mixed Rust C++ code, but I think it can also be useful for certain kinds of pure Rust as well. I'd like to make examples of both more readily available to motivate this kind of API more. In the process of developing this, I sort of realized that pins docs don't express all of the things you can do with it. It only expresses a certain subset of it. I'd like to improve the documents so that they more clearly state the guarantees and what they mean for API design. I have a working version that I'm hoping to propose to the Rust standard library at some point. Finally, there are tons of C++ features that can make working with constructors easier, such as syntax trigger from being able to have struct literals, using constructor operations as an expression rather than as a binding. There is a very long list of these things that I'd like to that I'd like to port someday in order to make constructors easier to use. Now, none of this would have been possible without the help of many people who I've discussed this feature with, who suggested ways to make it more concise, who pointed out flaws in the original design. However, I want to especially thank Tyler Mandry. After he corrected something I asserted about pin, I realized that the pin guarantees could be used to express constructors. I'd also like to thank Manish Gorgokar, who encouraged me to publish this idea widely for the benefit of both Rust C++ interop and the development of Rust in general. Thanks for listening, and I hope you enjoyed my talk.
Hi everyone, I'm Danny Osorio from the Developer Relations team at Near Protocol. Near is a next-gen carbon-neutral blockchain backed by investors such as A16Z, Electric Capital, and Idea Collabs. All smart contracts on Near are written in Rust. It's based on the proof-of-stake consensus mechanism, so Near is approximately 99.9% more energy efficient than Bitcoin. We've also partnered with South Pole Global to measure and offset all emissions, making us the very first climate-neutral blockchain. We're definitely the new kid on the block, but our guiding philosophy is that crypto should be accessible to everyone. So we built a blockchain that's easy to build on and easy to use. In fact, my intern built her first Near app in just 6 days. We have a virtual hackathon series coming up that's called MetaBuild, and it runs until the middle of October. There's 3 main events, and across those we'll be giving out 1 million in prizes. All of which are paid out in Near tokens, which is the cryptocurrency that powers the Near network. Coming up, check out MetaBuild.
Welcome to the Metaverse, where a total of $1 million in prize money is up for grabs. Are you ready to build? Build with community members throughout the Metaverse or locally via 9 global hack nodes. And participate in workshops from industry leaders.
Before we get into our next talk, I want to take another moment to give a huge thank you to some of our Diamond Tier sponsors. Thank you to Solana, Hadean, Era Software, Near, and Google. RustConf couldn't happen without your support. And now, please welcome our next speaker, Lily.
Hi, my name is Lily. I've been using Rust for side projects since 2015 and professionally at OneSignal since 2019. I'd like to tell a short story about a new Rust user who runs into some stumbling blocks during their learning journey and use that to jump into a discussion about how the community can better serve users like them. Meet Gene. Gene is a Python developer who's been writing software for several years. They're working on some JSON aggregation code in Python, and they've noticed that it's a performance bottleneck for their application. They've heard that Rust is very fast, so they decide to investigate moving it into Rust. They find the Serday crate, which allows them to parse the JSON into easy-to-manage structs, and they're happy. The code seems pretty quick, and they proudly show it off to a more experienced Rust developer. The experienced developer tells Gene that the code is okay, but it has some unnecessary allocations in it. It uses an owned string on the data struct. It could be improved with the addition of lifetimes. Serday has support for deserializing borrowed strings instead of owned strings, so you can save on a lot of allocations, they tell Gene. Since they're excited about the prospect of writing high-performance code, Gene leaves this conversation with the motivation to dive deep. They haven't used lifetimes yet, but they do a lot of reading to try and figure it out. After a lot of time and frustration, they have a solution that should be much more performant. They've added a lifetime to the data struct that Serday is using for parsing. Gene benchmarks the performance of the new borrowing version against the original owning version. They run both of them against 1,000 lines of JSON. It seems like they made some meaningful performance improvements. The bars here represent the runtimes of the solutions relative to the fastest version. The fastest version is the Rust code using references, and the slower version is the Rust code using owned strings. This runs in around 1.5x the time of the faster version. Out of curiosity, Gene also benchmarks the original Python code against both Rust versions. Oh. After seeing these benchmarking results, Gene is a bit confused. They just wanted to write something that was faster than Python after all. Their original slow version is nearly 20 times faster than the Python code, so why did they have to spend all that time learning these new topics? Now, it may not seem like it if you've been writing Rust for a while, but there are a lot of new ideas hiding in this struct definition. If you wanted to understand this as a new Rust developer, you would need to learn about lifetimes, which implies learning about generic arguments and references. References implies learning about ownership. Ownership is famously one of the most difficult things for new Rust developers to learn. Now it's just one of 4 difficult topics that's facing Gene if they want to be able to graduate from writing so-called slow Rust code. This is also an extremely simplified example, where Gene parses the data into a struct and immediately uses and discards it. If this were a larger example, they would need to add lifetime annotations to function parameters and return types, impl blocks, and add them to any structs which contain instances of data. They may spend a long time threading all of the lifetimes through, only to find out eventually that they can't do it because a function somewhere in the program does not accept input that uses borrowed values. Lifetimes and generics are viral complexity for programs, and adding them in one small place deep within the call stack can sometimes require adding them to tens or even hundreds of other places in the code. Now, at this point, there are a few ways that our story can go. Gene might see the value of the new skills they learned while tweaking the performance of their code. They may have found the novel memory model of Rust interesting and be intrigued to learn more. They might also think that they spent a lot of time learning esoteric concepts only to get an improvement that wasn't significantly better than what they were already getting from their so-called bad code. They might not see the long-term benefits of these things and focus in on the small performance difference relative to the large effort they put in. Different people will of course have different reactions in the same situation. But I would like to propose the idea that Gene might have been able to delay these topics to a bit later in their Rust journey. Now, I don't mean to make these topics out to be unapproachable terrors, but they do have a very real learning cost to them, and presenting them as something that new developers need to tackle head-on soon after starting increases the demands on new developers and puts barriers in place that can have negative repercussions throughout the community. I'd like to propose instead that we encourage new Rust developers to write more easy Rust, or you might even say bad Rust. We should be encouraging people to write functions like this. This function uses two owned strings when it could very easily take in two borrowed strings. These borrows can be added on when it's really necessary. Now, an experienced developer might be able to determine when and where these kind of borrows can be effectively used without having large effects on the program's complexity. A newer developer might try to add lifetimes and borrows to every heap allocated type in their code and get extremely frustrated. I think we should all consider how Rust looks to a new developer. This is a language that has a reputation for being very difficult to learn, even for experienced people, and I don't think it needs to be that way. New developers can sidestep a lot of the difficulty of the ownership and borrowing system by writing code that is slower to run, but easier to understand. This trade-off between performance and ease of use is not unique to Rust at all, but Rust does have the unique benefit of naive code often being fast enough. We should be taking advantage of this benefit and leveraging it to allow new Rust developers to become productive with Rust more quickly. These new developers might not be writing code that's as fast as possible, but it will often beat dynamic languages, and they should be more likely to stick with the language if they don't have huge barriers to adoption. These topics are not going to go anywhere. They will always be there for the developers that really do care about performance, but the majority of people trying out Rust for the first time can get away without them. I'd like to close with a few tips that I think we should more quickly provide to new Rust developers. Firstly, pass around own values and not references. References are great, but they can open up a can of worms that many people are not expecting. Next, use clone. You can save on heap allocations by borrowing, of course, but does your 100-line CLI program really need to save on allocations? Maybe not. If you do find yourself in a situation where you need to save on heap allocation work, maybe try wrapping your type in an RC or an ARC instead of standard references. These are reference-counted pointer types that allow you to share ownership between multiple variables, similar to how values work in garbage-collected languages. Finally, and this one's important if we want to hide the performance costs of the previous points, compile your code with the release flag. If you spent any time on Rust communities like the subreddit or Discord servers, you've probably seen someone complaining about Rust being slow, only to then become impressed with the performance after recompiling with optimizations turned on. Thank you, everyone. I hope that this talk inspires you to write less heavily optimized Rust code and new developers to not worry so much about the performance. If you're interested in speeding up your non-Rust projects through incremental addition of Rust code, check out my book, Refactoring to Rust. The first 4 chapters are available now in early access on Manning.com.
Hi, my name is Pei Xin, and I'm representing Huawei sitting on the Rust Foundation board. Rust is a very important technology which we think will play important role in the critical information infrastructure development. It provides good balance between performance and key techniques to tackle memory-related cybersecurity problems. We are very happy to work with all of you in this vivid, diverse, and global community, and we all together to make this technology more sustainable.
Huawei invites Rust as our friend to solve some long-standing technical problems, making our software system more trustworthy, usable, and useful. After adopting Rust as a memory-safe programming language, some of our products for telecom infrastructure become safer and more performant, which of course is just a beginning. We are also developing engineering tools to make such a transition easier and smoother. For these achievements, we give credits to the great and vibrant Rust community, which lends tremendous help to our pull requests and answered our technical questions. As a friend, we are also determined to contribute back to the Rust community more substantially in the coming years. Enjoy the Rust conference.
At AWS, we believe leaders create more than they consume and always leave things better than they found them. The two features of Rust that we believe are most important are security and sustainability. The memory and concurrency safety of Rust make it possible for AWS engineers to build great customer experiences quickly and safely. And Rust's low resource requirements make it possible for AWS engineers to build more sustainable solutions. Rust has quickly become critical to building infrastructure at scale at AWS. Firecracker, Amazon's first notable product built with Rust, launched publicly in 2018. We use Rust to deliver services such as Amazon Simple Storage Service, Amazon Elastic Compute Cloud, Amazon CloudFront, and more. AWS didn't start Rust or make it the success that it is today, but we'd like to contribute to its future successes. AWS has been a proud sponsor of the Rust project since 2019, and in 2020, we started hiring Rust maintainers and contributors. AWS is excited to partner with the Rust project to build secure and sustainable solutions. Together, we can create technology and community that outlast us all.
As we all know, when it comes to Pokemon, you gotta catch them all. But what do you do when you don't know what Pokemon cards are in your collection? Well, our next speaker is going to tell you how they found out. Please help me welcome to the stream, Hugo.
Hi everyone, my name is Hugo Peixoto, and I'm here to talk to you about my Pokemon collection. I've been collecting these Pokemon cards for a while now, but I never really took the time to keep them organized. And recently I started playing the game again, so it has become a bit of a problem. Because every time I want to build a new deck, I need to know if I have the necessary cards to do it or if I need to go out and buy something. So I decided to fix this. I started by building a website where I could go and manually enter how many cards I have of each, and that would get saved to a database. Now, this worked fine, but I wanted to try something different. I wanted to have a webcam pointed at my desk and put a card in there and have the software automatically detect which card it was and store that in the database. So this talk is going to be about the algorithms that I used and the problems that I faced. Here's a very high-level overview of the whole process. We start by grabbing a frame from the webcam's video stream. Then we take that frame and we need to extract the card image from it. And finally, we go through a dataset of known cards and search for the one that's most similar to the card image we just extracted. And we add that to the database. Now, initially, I was working with frames like this one on the left, and you can see that there are some shadows, and the wood pattern of the desk causes some noise as well. So these things were making my life a bit harder than I wanted. So I moved to a more controlled environment, like the picture on the right. And there you have a white background and there are no shadows, and things worked much better under these conditions. Now, I mentioned that I needed a data set. So there's this website, PokemonCards.com, and they have pretty much all the cards in there that were ever printed in English. So since they don't have an API, what I did was I built a Ruby script that just scraped the whole thing and downloaded every card image to my computer. So I ended up with about 14,000 cards. Now let's focus on detecting and extracting the card image from the frame. We're working with 1080p color images. You might think of a color image as having three channels, the red, the green, and the blue one. Now, what I found is that most computer vision algorithms only really care about the brightness of the pixels, or how light or dark each pixel is. This is equivalent to working with grayscale images, and that's what we're going to do. Now, once we have this grayscale image, we want to crop it to the boundaries of the card, while also fixing its perspective so that there's no rotation or skew. We want it to become as close to a 2D scan of the card as possible. And the first step that I did to do this was to apply a Sobel operator. The Sobel operator highlights the edges of the image, both the outline of the card and the edges in the drawing itself, and it removes any sections of solid color. Since we're looking for the boundaries of the card, this helps highlight the edges, particularly in cases where the card doesn't have a thick black border like this one around it. Some cards have a yellow border, and this helps to normalize the levels a bit. Now, how does the Sobel operator work? It's a kernel-based image filter, and what that means, it's an image filter that follows a specific structure. So you calculate each pixel independently of each other, and you look at the respective pixel on the source image plus a small window around it. And in this case, I'm showing a 3x3 window, but it can be a window of any size. Then you take the pixels in that window and multiply them by a matrix of coefficients. And that matrix is called the kernel. You sum all those values together and you get the resulting pixel. The kernel is what defines the behavior of the filter. So if you want to apply a Gaussian blur, which is a common operation in many image editing programs, you use one kernel. And if you're applying the Sobel operator, you use a different kernel. So if we apply the Sobel operator to every pixel on this image, we end up with something like this. The values here range from 0 to around 1,000. And to better understand what's going on, let's map this to a grayscale image, where the zeros become white and the thousands become black. Here you can see that the corners and the center of the image are completely white. And this indicates that there's no edge in those regions. While around the circle, a dark ring has formed. And that indicates that these pixels likely contain an edge. So if we apply this to our initial grayscale image, we get this. The next step is to find the contour of the outline, or the outline of the card. I did this using a simple algorithm. We scan each row from left to right, and when we hit a pixel that's above a given threshold, we stop. We mark that pixel and move to the next row. So if we do this for every row, and then we do the same thing from the other side, and from the top to bottom and bottom to top, we end up with these marked pixels. So this is the contour of the image. And this works because the card doesn't have any holes or any concave structures or anything like that. And once we have this, the next step is to turn this contour into 4 straight lines. And we do this using an algorithm called the Huff transform. Now let's see how that works. So we go through each pixel on the contour, and we draw all the lines that go through that pixel. Not literally every line, because that's an infinite number of lines, but we pick a resolution like every ½ degree or something like that, and we draw those lines. So in this case, I'm drawing 8 lines here. So we start those lines, and then we move to the next pixel, and we do the same thing. And you'll see that there's one common line between the two sets. If you take a look, the horizontal line happens twice. And since this line occurs more times than all the other ones, it's more likely that it is a real line. So we're going to do this for every pixel on the contour. And we're going to keep only the lines that occur, let's say, 200 times or something, and discard all the rest. So if we take those lines and draw them, we get this. And it's pretty close to what we wanted, but not quite there yet. So to get rid of this extra noise, what we can do is we can cluster these lines together and average them out. So any lines that are similar enough get clustered together. If we do that, we get our intended result. So with these lines, we can calculate their intersection points. We can just do this by going through every pair of lines, calculate their intersections, and discard any points that fall outside of our image. And these 4 points, what they represent is the 4 corners on our card. Now that we have the corners of the card, we can work on fixing the perspective to get something like this. And this transformation is done, roughly speaking, by taking each pixel and moving it to another coordinate. And this movement is done by multiplying each pixel's coordinate by a matrix obtained by solving a system of equations that's based on those four corners. And to do this, I used a crate called N-algebra. They implement a bunch of linear algebra algorithms. So doing that, we finally got what we wanted, which is our 2D card image. Now we can take this image and search for matches in our data set. Since each image has around 1 million pixels, we can't really compare them directly. Since there are 14,000 cards, this would take forever. So we need to reduce the amount somehow of information that we're comparing. And we're going to do this using a perceptual hash. And what a perceptual hash is a smaller representation of the image that still keeps the essence of the image. The main idea is that similar images will have similar perceptual hashes. So we take each card on the data set and convert it to its perceptual hash. And we do the same thing for our image that we're searching for, and we compare those instead. So in this case, I picked a 16 by 16 hash. That's 256 bits or 32 bytes. And comparing that is fast enough. So let's see how this hash is calculated. We take our image and resize it down to 16 by 16. And then we need to binarize it, convert each pixel into a 0 or a 1. And in this case, what I'm doing for that step is each pixel becomes a 1 if it is darker than the pixel to its left, and it becomes a 0 otherwise. And there are different types of perceptual hashes, both in the resizing part and the binarization step. But this is a simple algorithm that gave me good results. So here's an overview of the full process. We take the original image, we grayscale it, and apply a Sobel operator. And then we find the contour, extract the 4 lines that represent it, calculate the 4 corners of the card. With that, we can fix the perspective of the grayscale image and apply a perceptual hash. Now, this process gave me pretty good results, but there was one case that I needed to deal with. These cards over here. They look the same, they have the same name, the gameplay effect is the same, but there's one small difference. They were printed in different sets throughout the years. And you can see that the set symbol on the corner there is different. So I need to be able to tell these apart. The set symbols are so small that the perceptual hash doesn't pick up any differences in there. So I needed to find a different way of doing this. So I implemented a technique called template matching. I created individual images for each of the set symbols, and we go through each possible position in that marked zone in the card there. And for each position, we compare the set symbol with the pixels of the card. And if that error is below a certain threshold, we consider it to be a match. I had to use a different threshold for each set symbol because some of them are more complex than the others, and I had to tweak this a bit manually. And this solved my problem. So with these two techniques, I was able to get a good detection rate. So let me show you how this works. When I place a card there, you'll see that the card on the left, that's the one that's being detected. And this works even for noisier cards like this one. And in this case, you'll see on the left that the set symbol is also being detected. So let me show you a case where the set symbol makes a difference. This Marnie here, it belongs to the Champion's Path expansion set. And you'll see that the correct symbol is shown on the left. There's another Marnie, which is printed in a different set. This one was printed in the Sword and Shield base set. And you can see that it also gets detected correctly. Now, there are some cards where this doesn't work so good, like this one. It's a foil card, and that means that there's a lot of reflective material in it. So the lights form all these bright patterns, and the perceptual hash just isn't able to deal with it. Now, to finalize, here are some of the libraries that I used, and some that I think that are worth checking out. The last one, RustCV, is an organization with many computer vision algorithms. So if you're interested in the area, I think it's worth checking out. They also have some basic tutorials going through some of them. And the code for this is available on my GitHub account. So if you want to go and check it out, feel free to ask me any questions. And that's all I have for you today. So thank you for listening.
Thank you, Hugo, for that wonderful talk. In just a moment, we're going to take a break for lunch, but first, I need everybody's help. I want to see all of you get those crab claws in the air as we summon to the stream the mighty Ferris. Ferris, 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 Ferris.
Ferris, 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 Ferris.
Ferris, 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 Ferris.
Ferris, 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 Ferris.
Ferris, 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 Ferris.
And with that, we are going to take a break for lunch. We'll be back at 1:30 p.m. Pacific time. If you're looking for some friends to eat lunch with, there'll be plenty of groups forming in Discord. See you soon. Say bye.
Hey folks, I'm Anatoly, CEO and co-founder of Solana Labs. So we've been building in Rust for about 3.5 years. None of us were really Rust devs before we started. And looking back in our time, we feel like Rust was really just such an amazing choice for us to pick. The tooling like Cargo and the borrow checker and the compiler and the way that the compiler treats critical sections between threads really allowed this distributed team of great engineers to communicate through the language and build as fast as they could and not worry about the classic set of bugs that you see in C, C++, and Java. So we couldn't be more grateful to the Rust community for the tools that they've built. And we've gone full in on Rust. The programming environment that we created where developers write applications, that's a custom toolchain for Rust that targets Berkeley packet filter. So if auditing code or building high-performance, mission-critical operating system code is something that you're interested in, please check out our jobs page, because not only are there openings at Solana Labs itself, there's, I think, over 50 ecosystem partners that are looking for Rust engineers. Hey folks, this is Anatoly. I am co-founder and CEO of Solana Labs. We're really proud to be a sponsor of RustConf. It's been an amazing tool that helped us build a high-performance, low-latency blockchain over the last 3.5 years. None of us really were Rust devs before we started. And without Rust, I don't think we would have gotten here because of the high performance and the safety that the compiler provides. It's just been kind of our secret weapon when building applications. So we want to thank this community and we want to see it grow. And if you're a Rust dev that is interested in building high performance systems, software, or building financial applications or experimenting with blockchain, please check out Solana.com. So you should find job postings from us or from our ecosystem projects that are building smart contract applications. Or in the hackathon, teams are forming right now. So if you want to just see what it's like and participate and see if you can win a prize, just jump right in. We have a really friendly community. Everyone loves Rust, and we'd love to be a bigger part of the Rust community in general. So thank you so much.
Hi, we're EdgeNode, the creators of the Graph, a crypto protocol for organizing and serving blockchain data in a verifiable way. So, why are blockchains so important? We're at the beginning of a transition in changing how humans cooperate and organize. The internet changed how humans communicate, but the software we use for coordinating on the web is owned and controlled by giant corporations. Crypto gives us the tools we need to communicate, make decisions, and distribute resources in a decentralized way. The Graph is a core protocol for enabling this. People call us the Google of blockchains. Our core software is written in Rust, and we're hiring Rust developers. If you're into writing high-performance, secure code for processing vast amounts of data, this could be a great chance to work on a distributed team with passionate people working to build a more vibrant, decentralized future. Apply today at edgenode.com or thegraph.com.
Well, I hope you all had a good lunch. We're back with a great afternoon slot of talks lined up for you. Please help me welcome our first speaker of the afternoon, Midas. Hey, Tess. They turned me into a crab again. Can you help?
Hello everyone, I'm Midas Lambris and I'm here today to talk to you about fuzz-driven development, when you know and you don't know. So, first of all, who am I? As I said, I'm Midas Lambris, and by day I'm a senior software engineer for the refueling solutions, and by night I'm a Rust enthusiast. I also have various social media on which you can find me. I'm not the most active person, but if you have any questions or just want to chat, you can reach me on these. For the people attending RustConf, you can also reach me right now in the Discord if you have any questions or if anything is unclear. So for the subtitle, when you know and you don't know, this refers to one of the strengths of fuzz-driven development, that even with a minimal amount of domain knowledge, you'll still write decent software without any major mistakes, because fuzz-driven development will guide you through it and you'll learn as you go without having to fear that you've just made a big whoopsie. You only need to be able to come up with one simple thing, some invariant, and the rest you'll learn as you go. But to understand fuzz-driven development, we first of course have to understand what fuzzing is. So fuzzing, according to the Rust Fuzz book, which is an excellent resource for anyone getting started with fuzzing, fuzz testing is a software testing technique used to find security and stability issues by providing pseudo-random data as input to the software. So basically what it's going to do, it's just going to come up with random data and give that as input to your software. And then it's going to monitor your software for some things. Most of the time, it's going to just see if your software crashes. If it crashes, it'll report that back to you that for this input, something crashed. There are other variants. Sometimes it will keep fuzzing indefinitely and just collect crashes. And then when you say, okay, you can stop running, it'll report them all in one go. If that's not clear yet, we'll see also a bit of fuzzing later on once we go through an example, and that should clarify it for you. Okay, so we have fuzzing, now fuzz-driven development. So fuzz-driven development is a 6-step process, of which the first one is determine an invariant. So that was a C that I was referring to earlier, the one thing that you need to know. This doesn't always need to be correct. You can start with an incorrect invariant. You just need to be able to come up with a starting point. Second step, you provide a fuzz target that expresses that invariant for you. Fuzzing target sits between the fuzzer and your software, which can do a bit of manipulation on the data before passing it along to your software. Then we're going to run the fuzzer until it gives us a failure. And we're going to think about why did this fail our software? Why does this cause a crash or whatever? And then depending on our reflection, we might just have to write some new unit tests and do some development. And then step 6, the final step, is a non-final step because it's iteration. You're going to restart again. Most of the time, certainly with more mature projects or when you've been doing fuzz-driven development for a while, most of the time you're just going to return to step 3, run your fuzzer again until it finds another failure, another bug in your program. Sometimes you also notice that this doesn't really make sense if you reflect on it, and that might be because your fuzzing target doesn't really express the invariant that you want. So you might have to change your fuzzing target. Sometimes you'll even, after the reflection, see that your invariant actually doesn't make sense or isn't very good. So you have to change the invariant. So these are the 6 steps of fuzz-driven development. Now, let's try to map this on where where in the wild you'll find most fuzzers today, or fuzzing targets today, and that's on parsers or compilers. So the first one is determining an invariant. For a parser, most of the time this is going to be, it shouldn't panic. It should either return an error or an okay, but it should not panic. Also goes for most compilers. It should accept or reject, but it shouldn't crash. Then a fuzzing target that expresses this invariant, you just take whatever input the fuzzer comes up with and you pass that along to your parser. You don't even care about, okay, our error just doesn't crash. Then we're going to run the fuzzer until it fails, which in this case means that our parser crashed somewhere, that it panicked somewhere. And we're going to think about why. Most of the time this is just some path you missed or something like that. But since we have a pretty simple fuzzing target and a pretty simple invariant, it's very unlikely that it's going to be one of those two. So you're going to write a unit test for this input, which just gives this input, so that your test coverage increases, and then you develop such that the test passes. And you iterate again, in this case most of the time, back to step 3. So now that we know fuzz-driven development, or have seen it for a bit, we're going to write a library which by using fuzz-driven development to develop it. The library that we're going to write is a JSON patch squasher. Most of you will know what JSON is, but what is a JSON patch? So assume we have this JSON document to start with. 2 properties, a name with the value mids and a ranking 8. Later on, the user gains some popularity. His ranking goes up, he goes to rank 5. Okay. He gains some more popularity, a bit more. His ranking goes up to 4. These changes, we can express them as a JSON document itself. So the change from ranking 5 to 4, we can say, and as a JSON array, there's an operation there to replace /ranking, so that property from the root, with value 4. Again, if the user, for example, changes his name, and by consequence his ranking drops a lot, there's another JSON patch for that change, one to change the ranking to 950 and one to change the name. Those are two patch operations, and this is one JSON patch. That array is the JSON patch. The entries in it are the patch operations. So then again, another change, the ranking shoots up to 1, he did something amazing. Another JSON patch, an array with one operation in it to change the ranking to the value 1. So those are JSON patches. Now we know what JSON patches are. Now the squashing part. So if we have our operations from before, our JSON patches, we can express the same effect from that starting document to get to the same end document shorter. So in this case, we can express the same thing from the same starting document to get to the same end document by just replacing the ranking with 1 and the name with Midas. And that has the same effect scoped out on these documents, on the starting document. And that's the squashing operation that we're going to try to do. So now we know what we're trying to write. Okay, that's what our library is going to do. It's going to take this squashing. It takes a set of patches and it tries to minimize it a bit. So the library is going to look like this. We have a public function which takes the patches and that's going to forward basically to squash operations, which takes an iterator over all the operations and all of the patches. And for now, we're just going to leave to do in there, so we don't have any logic yet. And this is our starting point now. So this is what we're going to use for fuzz-driven development. So step 1, we're going to write an invariant. We're going to come up with an invariant. And then this is what I said before. The effect should be the same. So the effect of applying the squashed patch should be the same as applying all the patches that were squashed in their order. That's the invariant. This is then if we do this, it's still correct. It's still, the squashed is still doing the same thing. So step 2, the fuzzing target. This is what it looks like for cargo fuzz. Fuzz target, exclamation mark. Then the data is what the fuzzer is giving you. So we take what the fuzzer gives us, the data, and then we're going to see if it matches an input struct, if we can deserialize it into our input struct. If it can, okay, great, we'll return that and we'll return that, assign it to the input variable. If it doesn't, then we return from this function, from this closure, so such that the fuzzer itself will mutate again and try the next iteration, because we can't make sense of what it has given us. The input struct itself is two things. One, starting value, so we can apply patches to it to see if our squashed patch does the same, and then the patches themselves. So if we have that, then we're gonna squash the patches from the input. That's what our library is gonna do. And then we're gonna apply the patches in order that we've been given them, that the fuzzer has generated for us to get our normal result. And then we're gonna apply our patch to the starting value to get the squashed result. And then we're gonna see if they're the same. They should, because it's the same effect, the end documents should be the same. So this is our fuzzing target in this case. So step 3, running until failure. If nobody has ever seen it, this is what it looked like when you start a fuzzer. I sped it up with a factor of 100 because this took a while. But I'd like to draw your attention again to that we still don't have any implementation. We still have to do in there. And by showing this, I'd like to show that fuzzing can only show the presence of bugs and it can't show the absence. So it can come up with counterexamples of where we fail to uphold our invariant, but it can't guarantee us that we're upholding the invariant. And what I'm trying to show here is that duration of the fuzzing before it fails does not equal quality, sorry. Because again, we still have that to do in there. So, step 4, reflect. Well, it took a while to get our first crash, so it's difficult for the fuzzer to come up with the input struct that we expect. There are some other ways around this, structure-aware fuzzing, you can read about in the fuzz book, Rust fuzz book. You can seed the fuzzer with some data, but that's outside of the scope of this talk. And then this is for brevity. Normally this would become obvious after a few iterations, but I'm gonna already do it here, is that the start state and the patches don't always make sense together. For example, after a while you might come up with something, the fuzzer might give you something like this, that you have a name and a ranking, and then it's the operation, the patch is remove a non-existing property. If we do this in our fuzzing target, it would fail because we cannot apply the patch to the document. So it's not gonna fail because we do something wrong or our library can be 100% correct, but purely the patch doesn't make sense on the document. So that's what we reflected about. This is a bit of a shortcut to get you to come along with the next steps because they are a bit more important now. So we're gonna iterate. So we saw that, yeah, we have some problems with our fuzzing target, but it could also be that our invariant isn't that great. So let's take another look at our invariant. So what we had was the effect of applying the squashed patch should be the same as applying all the patches that were squashed in their order. This doesn't express anything about what we're actually trying to do, the squashing. I basically can return one patch that's all the other patches together, and that would still have this invariant. If we can come up with an invariant that also expresses, besides the effect that it should minimize it, then we'll have a better progression through our fuzz-driven development. So as a keynote among you might have noticed earlier on the example, is that if you take the initial document and the end document and you calculate the patch between those, that you have the minimal diff that we can squash towards. If we have all the other ones, the beginning and the end, that's the minimal one. You can't do a shorter expression of the difference between start and end than the difference between start and end. So that's our goal. That's what we're trying to achieve. So that's what we're going to compare against. We're no longer looking at the effect, but we're looking at the patch itself. So to pour this into a fuzzing target, step 2, we no longer try to deserialize into the input struct. Now we're deserializing into a vector of consequent JSON values, such that we ourselves can calculate consequent patches between them. So again, if we can do this, we continue. If we can't, we return fuzzer will mutate again because we don't crash. And gives us a next input that might be deserializable. Also again, because we're gonna calculate patches, if we only get 1 or 0 document, we can't calculate subsequent patches, so we're not gonna be able to do anything with that. Same story, just return such that the fuzzer will mutate again. Then we're gonna do that actual calculation to get all the patches between all the documents. And we're also going to calculate what I'm calling the global patch, the one between the first one and the last one, because that's the one that's minimal. That's the one that we're going to compare against. And then we're going to squash the patches and then compare. There's a bit more boilerplate here because our library if you have 0 patch operations, it will return none instead of a patch with 0 operations. So that's a bit more boilerplate, but it's just comparing the minimal diff with what we squash into. So now we're gonna run until failure, and then after a while, this is what we're gonna be greeted with, that the thread unnamed panicked at not yet implemented, because still we have that to do in there. And then we're also shown what input caused the failure. And if we zoom in on that a bit, we can see that it's 2, 1, an array of 2 and 1, new line, tab, new line. But for us, only this is important, an array of 2 and 1. So first document is 2, the second document is 1, and that the fuzzing target will calculate a patch between them and give that patch, because there's only 2 documents, so 1 patch, give the patch to our library, and then we'll hit to do. So let's reflect a bit. Might actually help to write something that does something instead of leaving to do. So an actual implementation might help. So we're gonna take whatever the failing input was, in this case an array of 2 and 1. And what I like to do is write an helper function that basically does the same as a fuzzing target, such that I can write these very neat, very tiny unit tests very quickly by just copy pasting that input from the fuzzer into here. So this is our first unit test. Our logic now is just to do, and minimal thing that we can do to make this pass is just return all of the patch operations as a vector, and that would then result in the unit test succeeding, and we can iterate again. So we again run until failure. This time we have a bit of a bigger error message at the end, but the important parts are the assertion failed message, so the left versus the right, with the global patch versus the squashed patch. And at the bottom again we have the input that failed. So now we have 3 consequent documents of a number 44, a number 4, and a number 7. And then if I tidy this up a bit to make it a bit more readable, the global patch would be replace the root with number 7. What our library right now returns is replace the root with 4 and then replace the root with 7. So let's think about this a bit. So I see that if the path is the same, that I only need to care about the last one. And we still have 2 operations, but the first one has the same path, and it's the second one that basically still has an effect at the end. So when multiple operations are there for the same path, we only need to keep the last one. So we again pour this into a unit test. Again, same thing, only the input needs to change this for this, and another name, of course. And then we develop. So our implementation, instead of just collecting into the vector, now we're gonna use a hash map from the path to the patch operation. Loop to all operations and insert them by their path. And yeah, if you insert something that already exists, then it is going to be overwritten in the hash map. So then to get back into our vector of patch operations, we just drain the hash map and only care about the patch operation. The paths that we use as keys, we can drop them. We only need the patch operations as a vector, so we collect it again. So this will make our unit test pass again. So we can iterate again. We can run it until failure. This time, this is what we'll end up with. The failing input would be 4, an array with 2 inside it, and an empty array. The global patch here will be replace the root by an empty array. Our squash operations will still return replace the root with an array with number 2 inside of it, and then remove the first element of the root. So here we see that our previous assumption still holds, that the same path needs to be squashed. because this one is talking about a different pod. So for a different pod, we still might have to squash. So that's our reflection. Even if the pod is different, we might still have to do some squashing between them. So we write a unit test again, and then we develop. This is way too much code to show you, but the main idea is a user radix tree, which can give you keys, so the pods, which are parents or prefixes of the pod you're currently looking at, or all the keys which start with the prefix that you give it, so basically children potentially of what you're using. And then you have all sorts of combinations you can get into. I'm not going to show it here for brevity's sake. But after you've done that and unit test passes, we're going to iterate again. I know, fun times. So we're going to run it until failure. This time our failing input looks something like this. An empty object, 0, an empty object. The global patch is going to be empty because you're going to compare an empty object with an empty object. You don't need to do anything. Our library will return that the squashed patch is a replace operation with the root path and replace it with an empty object. So our previous assumptions still hold. This is all operating on the root path. But if you think a bit about this, and more in terms of the patches, is that the patches don't contain any information where you come from. If this initial document, this empty object, was anything else, we would succeed. And then the patch operation would be, the squashed patch and the global patch would be the same again. But yeah, the JSON patches don't contain any information from where you started. It only describes where you go to. Like you start from something and you replace it with, and then that value is contained in the patch. What value you started with is not contained in the patch. So here actually we can realize that the patches themselves don't contain enough information to always come up with a minimal patch, because we don't know what you start from. So that's our reflection this time again. Sometimes it's impossible to get that minimal diff solely from the patches. You'll need the starting document as well to be able to come up with that, that minimal diff, the minimal patch. So we have two options now. We can either change our libraries API so you'll have to pass in that starting document as well, and that way we can guarantee that we'll be able to calculate the minimal diff. Or we can allow for suboptimal results if you find it more important that you don't have to give in the initial document. Based on what you want to do, you're going to develop some more unit tests or not, and you're going to iterate, because if you choose one of those options, you'll have to come up with a new invariant, because for the second one, the allowing suboptimal results breaks our invariant, so we'll have to come up with another one or do some conditions on our invariant. So what we've been doing, again, the 6 steps of fuzz-driven development: you determine an invariant, you write a fuzzing target that expresses an invariant, you run it until failure, you reflect on that failure, potentially develop and do some unit testing, and then you iterate again. Those are the 6 steps of fuzz-driven development. So why does this work? Well, why this works is because what we're doing on a broader scope than the 6 steps. So what we're doing is basically we are using a non-cognitive process, fuzzing, so the fuzzer software, which is a program, that to drive and guide our cognitive development of software. And we just need to provide a simple seed and invariant. So we start with a little bit of cognitive work, and now we let the fuzzer guide us and show us where we're lacking in our invariant, implementation, expression of our invariant. So why this is good, or why you might want to use it, is because the cognitive gaps that you might have, if you have limited domain knowledge, they get less chance to manifest because you're not driving what you're gonna implement next. Is the fuzzer that's gonna show you here there's still something missing and you need to take care of it. So for example, you might not have, or I didn't think about the different pods still having to be combined together for a minimal patch, or that you might have to provide the starting document to be able to give that minimal patch in some cases. Those are things that are important to know if you want to write a good library, but I didn't know those, and I'm not sure if any of you already saw those or could think of those. So with a very limited domain knowledge, we've still written a library which already does a lot, and we don't have to be afraid that we've embedded some of our lack of knowledge in there, which will come back to bite us in the ass later on. So with that, I hope that I've given you a new tool to put in your developer arsenal, which is fuzz-driven development, and I hope you have fun at the rest of the conference. And if you still have questions, I'm still in Discord, so maybe talk to you there. Bye everyone.
Open source technologies have become a foundation for innovation and scale. Open source can help achieve reliability, continuous availability, and performance. However, designing and implementing the right tools and development environments to support these technologies can be complex and time-consuming. At Instacluster, we help you with this and so much more. Our managed platform can help you embrace the power of open source technologies and achieve scale and availability without sacrificing performance. With many globally recognized brands relying on us to build, deploy, manage, and scale their next-generation applications, our platform is a single destination to manage your data infrastructure. You can deploy open source data infrastructure technologies including Apache Cassandra, Apache Kafka, Apache Spark, and more on our managed platform across all major cloud providers with no vendor or technology lock-in. You can provision multi-region and multi-provider clusters in minutes through our management console. We're SOC 2 certified, and our team of experts are monitoring and supporting your infrastructure 24/7. Simplify your operations with one managed service provider for your data infrastructure environment. Power your enterprise with the Instacluster managed platform. Instacluster, reliability at scale.
It's that time again. Please help me give a huge thank you to our gold tier sponsors. Thank you to Informal, Instacluster, and The Graph. RustConf couldn't happen without your support. And now please help me welcome our next speaker, Isabella.
Hi, I'm Isabella. Today we're going to talk about how we wrote the fastest gradient-boosted decision tree library in Rust. First, a bit about me. I'm a founder at Tangram, where we build open source tools that make it easy for programmers to train, deploy, and monitor machine learning models. Tangram is written entirely in Rust, from the core machine learning algorithms to the backend and front end of the web application. You can check it out on GitHub or on our website at the links here. So what are gradient-boosted decision trees? Let's say you want to predict the price of a house based on features like the number of bedrooms, bathrooms, and square footage. To make a prediction with a decision tree, you start at the top, and in each branch you ask how one of the features compares with a threshold. If the value is less than or equal to the threshold, you go to the left child. If the value is greater, you go to the right child. When you reach a leaf, you have the prediction. Here's an example. We have a house with 3 bedrooms, 3 bathrooms, and 2,500 square feet. Let's see what the price our decision tree predicts. Start at the top. The number of bedrooms is 3, which is less than or equal to 3, so we go left. The square footage is 2,500, which is greater than 2,400, so we go right. And we arrive at the prediction, which is 512,000. A single decision tree isn't very good at making predictions on its own, so we train a bunch of trees, one at a time, where each tree predicts the error in the sum of the outputs of the trees before it. This is called gradient boosting over decision trees. In this example, the prediction is 340,000. Now let's talk about how we made our implementation fast. The first thing we did was parallelize our code, and Rayon makes this really easy. The process of training trees takes in a matrix of training data, which is n rows by n features. To decide which feature to use at each node, we need to compute a score for each feature. We can compute that score for each feature in parallel. With Rayon, it's as easy as changing the call to iter to pariter. Rayon will keep a thread pool around and schedule items from your iterator to be processed in parallel. This works well when the number of features is larger than the number of cores on your computer. When the number of features is smaller than the number of cores on your computer, parallelizing over the features is not as efficient. This is because some of the cores will be sitting idle, so we will not be using all the compute power available to us. Instead, we can parallelize over chunks of rows and make sure we have enough chunks so that each core has some work to do. Each core now has some rows assigned to it, and no core is sitting idle. Distributing the work across rows is super easy with Rayon as well. We can just use the combinator parchunks. Rayon has a lot of other high-level combinators that make it easy to express complex parallel computations. Next, we used Cargo Flame Graph to find where most of the time was being spent. Cargo Flame Graphs makes it easy to generate flame graphs and integrates elegantly with Cargo. You can install it with Cargo install and then run Cargo Flame Graph to run your program and generate a flame graph. Here's a simple example with a program that calls 2 subroutines, foo and bar. When we run Cargo Flame Graph, we get an output that looks like this. It contains a lot of extra functions that you have to sort through, but it boils down to something like this. The y-axis of the graph is the call stack, and the x-axis is duration. The bottom of the graph shows that the entire duration of the program was spent in the main function. Above that, you see that the main function's time is broken up between calls to foo and bar, and that about 2/3 of the time was spent in foo and its subroutines, versus about 1/3 of the time spent in bar and its subroutines. In our code for training decision trees, the flame graph showed one function where the majority of the time was spent. It boiled down to something like this. We maintain an array of the numbers 0 to n that we call indexes, and at each iteration of training, we rearrange it. Then we access an array of the same length called values, but in the order of the indexes in the indexes array. This results in accessing each item in the values array out of order. From the flame graph, we knew which function was taking the majority of time. So we looked at the assembly code it generated to see if there were any opportunities to make it faster. We did this with Cargo ASM. Like Cargo Flame Graph, Cargo ASM is really easy to install and integrates nicely with Cargo. You can install it with Cargo install and run it as a Cargo subcommand. Here is a simple example with a function that adds 2 numbers and multiplies the result by 2. When we run Cargo ASM, we get an output that looks like this. It shows the assembly instructions alongside the Rust code that generated them. Note that due to all the optimizations the compiler does, there's often not a perfect correlation from the Rust code to the assembly. When we looked at the assembly for this loop, we were surprised to find an imul instruction, which is an integer multiplication. What is that doing in our code? We're just indexing into an array of F32s, and F32s are 4 bytes each, so the compiler should be able to get the address of the ith item by multiplying by 4. And it can do this by shifting I left by 2, which is much faster than integer multiplication. Well, the values array is a column in a matrix, and a matrix can be stored in either row major or column major order. This means that indexing into the column might require multiplying by the number of columns in the matrix, which is unknown at compile time. But since we're storing our matrix in column major order, we could eliminate the multiplication, but we have to convince the compiler of this. We did this by casting the values array to a slice. This convinced the compiler that the values array was contiguous, so it could access items using the shift left instruction instead of integer multiplication. Next, we used compiler intrinsics to optimize for specific CPUs. Intrinsics are special functions that hint to the compiler to generate specific assembly code. Remember how we noticed that this code results in accessing the values array out of order? This is really bad for cache performance because CPUs assume you're going to access memory in order. If a value isn't in cache, the CPU has to wait until it's loaded from main memory, making your program slower. However, we know which values we're going to be accessing a few iterations in the loop in the future. We can hint to x86-64 CPUs to prefetch those values into cache using the prefetch intrinsic. We experimented with different values of the offset until we got the best performance. Next, we used a touch of unsafe to remove some unnecessary bounds checks. Most of the time, the compiler can eliminate bounds checks when looping over values in an array. However, in this code, it has to check that index is within the bounds of the values array. But as we said in the beginning, the indexes array is just a permutation of the values 0 to n, which means the bounds checks are unnecessary. We can fix this by replacing getMute with getUncheckedMute. We have to use unsafe code here because Rust provides no way to communicate to the compiler that the values in the indexes array are always in bounds of the values array. Finally, we parallelize that section of code. But is it even possible to parallelize? At first glance, it seems like the answer is no, because we're accessing the values array mutably in the body of the loop. If we try it, the compiler will give us an error indicating overlapping borrows. However, the indexes array is a permutation of the values 0 to n, so we know that the access to the values array is never overlapping. We can parallelize our code using unsafe Rust, wrapping a pointer to the values in a struct and unsafely marking it as send and sync. So, going back to the code we started out with, combining the 4 optimizations together, making sure that the values array is a contiguous slice, prefetching values so they're in cache, removing bounds checks because we know that the indexes are always in bounds, and parallelizing over the indexes because we know they never overlap, this is the code we get. And the results are great. Tangram's gradient boosted decision tree library is faster than leading open source alternatives. Thank you so much for listening. If you're interested in learning more, please check out Tangram on GitHub at github.com/tangram.dev/tangram. And if you like the project, please give it a star. Thank you.
Chad for the pizza, AJ for the movie, Jenny for the soda. All these people owe me money for all this overpriced stuff I'm paying for in San Francisco. If only I had a decentralized way of being able to send money to each other so I can have all our transactions nice and reliably recorded on a blockchain. Guys, in this episode of Blockheads, we're going to create Dcash, a decentralized Venmo in a way to be able to send each other transactions using the wonderful world of cryptocurrency. So sit tight and let's have some fun. We're gonna add these two cool little pipes here. Add space.
That's what I figured.
Sorry, I hate Siri. Plus the price. So we're adding on the price, which is a string, to the text memo and separating them by these two pipes. Then we're gonna add the word near. Example account 1, 2, 3, 4, 5. Try to send that 3 near tokens and say, sending you 10 money. Oh, sent. Cool. So it looks like it all succeeded. And you can even see the amount of near sent to this account.
I think we can all agree that the world would be a little bit better if we all rewrote our software that was written in C and wrote it in Rust instead. Well, our next speaker did just that. Please help me welcome to the stream, Brian.
Hello, and welcome to Whoops, I Rewrote It in Rust. My name is Brian Martin, my pronouns are he, him, and I'm a software engineer at Twitter. I've been at Twitter for 7 years, and I've been using Rust for 6 years. I've worked on a few open source projects in Rust, including a benchmarking tool, a systems performance telemetry agent, and now I'm working on a cache server. When I'm not at a computer, I'm volunteering with my local search and rescue team, and I'm training my dog, Riker, to find people who get lost in the wilderness. This talk is framed around caching, specifically distributed key value storage. You can think of it as the standard library's hash map, but over the network. Cache services are very high throughput and low latency. A single core can do around 100,000 requests per second with sub-millisecond latencies. Caches are used to store frequently accessed items so that we don't need to ask the database for the same thing again and again. This helps protect the database from bursts of traffic and can let the application get data more quickly since the cache is so fast. There are a couple common open source solutions in this space, including Memcache and Redis, which are both written in C. This leads me to Pelican, which is Twitter's caching framework that we want to use to replace our forks of Memcache and Redis. Pelican gives us a single codebase to produce multiple caching solutions and to easily experiment with ways that we can come up with solutions that leverage new technologies. We needed to add TLS support to Pelican so that we could encrypt traffic between the client application and the cache server. I convinced the project maintainer, who's my current manager, that we could probably use Rust to add TLS support to Pelican. I had the time to work on this, and I definitely feel a lot more comfortable using Rust than C. And we wanted to be sure that if we were going to do it this way, that we would be able to match the performance of the C implementation. There were some previous efforts that made me think this was going to be possible. Back in 2018, an engineer wanted to add a new storage library to Pelican and decided to try writing it in Rust. The idea was to use the core of Pelican and provide an FFI wrapper around the Rust storage library. This worked out pretty well. Development was quick, and having a hybrid C and Rust server was workable. This became the first commit of Rust into Pelican. Super exciting. Then in 2019, another engineer was a bit more ambitious and wanted to try using Rust for the actual server code. They decided to use Tokyo to write the async server runtime, but leverage the C components from the normal cache server for storage and some of the other foundational libraries. But this was pretty neat. It showed we could do a lot more advanced layering of C and Rust together in the codebase, and I was super excited to see that Rust could in fact play a larger role in Pelican. Performance of cache services is super important. As I mentioned earlier, we expect a single cache instance to support around 100,000 requests per second on a single core, with latencies below 1 millisecond. To ensure this, we typically apply some synthetic workload with a fixed request rate and record the latency for each request into a histogram. Our goal is to hit the highest throughput with the P39 latency below some threshold. The P39 is the 99.9th percentile of the distribution of all the request latencies. So why do we care about this P39 number, this 99.9th percentile? Well, if we only need to make a single request to the cache for some higher level request, then only 0.1% of requests are going to be above the P39. And this is called fan out. If we need to make multiple requests to serve some higher level requests, let's say that we want to load a user profile, that might need 10 cache requests to actually fulfill that higher level thing. With a fan out of 10, we multiply the percentage of our odds of seeing a higher latency. So whereas with a fan out of 1, only 0.1% of requests would see a latency greater than the P39, with a fan out of 10, 1% of requests are going to see the P39. For even larger things, maybe loading something like a home timeline, you might have a fan out on the order of 100. This means that 10% of the requests are going to see your P39 latency. The key takeaway here is that multiple cache requests for a higher level request causes us to see the tail latency more often than you think. And that makes us care about these percentiles that might otherwise seem like they're way far out in the tail and don't really happen that often. But with fan out, they do. So, we have this implementation of Pelican Twemcache, Twitter's Memcache fork, written in Rust from 2019. It's Memcache protocol compatible, it uses Tokyo and Async for its networking, and it uses the C storage library to provide the caching. So the question is, can we use this as a starting point to add TLS? First, we need to do performance testing. And unfortunately, we found there were some performance problems with this implementation. The throughput was about 10 to 15% slower. This means that we'd need 10 to 15% more instances to match the throughput requirements for the cache cluster. That means it's 10 to 15% more expensive to run. On top of that, the latency was 25 to 30% higher at the P39s. This means that we could potentially see timeouts and errors in production. To visualize the benchmarking results, here we're looking at a latency curve of the P39 latency on the vertical axis versus the throughput on the horizontal axis. The C baseline implementation is shown in blue, and the Rust implementation is shown in red. And what we can see from this diagram is that the Rust implementation has a higher latency throughout the whole range of throughputs. Additionally, we can see that the Rust implementation doesn't reach the same throughput as the C version. So this means that the Rust implementation is slower in terms of both throughput and latency. That makes it a pretty tough sell to use this in production. But Rust should be as fast as C for this. Let's see if we can make it faster by taking some steps back. A basic server that you might find in a lot of examples is called a ping server. It's a really simple server that just responds back with the text pong every time you send a ping to it. It has all the basics that you need for a network service, though. It accepts new connections, it parses some requests, in this case either a ping or a quit, and then either responds with a pong or closes the connection. So it's a super simple protocol. We start with a ping server because it allows us to prove out the performance of a design. We have all the same functional blocks as a real service, except we're just not storing any data. But we can add all the things we need in terms of connection and request handling and debuggability and metrics. This is also a great place to start thinking about adding that TLS support that I was supposed to be working on, to prove that the design could easily accommodate both plain text and encrypted sessions. Since I was concerned about making the performance match the C implementation, I wanted to try and make things as equivalent as possible. The C implementation was basically just using epoll on Linux, so we could use MIO as an equivalent and not need to worry about async executors at all. We'd also have a simple event loop just like the C version. To get to a prototype quickly, I used a bunch of foundational libraries that I had been using in other projects. This meant I could focus on getting something built out quickly with a pure Rust build. If I had problems, I could always switch to the C implementations later. I also added TLS support using boring SSL at this point, so I was sure my design would handle both plaintext and encrypted connections. And then we benchmark again. Just like the previous chart, we're looking at request latency versus request rate, and specifically looking at the P39 latency. We can see that these are pretty close. This looked good to submit a pull request and merge into the Pelican repo on GitHub. Feeling good about this, it was time to move on to what I was actually supposed to be doing. The real goal was to add TLS support to our Memcache fork, Twemcache. So let's try doing that. The primary difference between Twemcache and the ping server is that we have a much more complicated protocol. The Memcache protocol has a whole bunch of different requests with variable numbers of fields, and my main focus was on getting all that protocol handling correct and making sure that it performed well. So, in order to avoid having to think about the storage aspect of this, what I did is I made a thin wrapper around the standard library's hash map and used that as a stand-in for the storage library. So this allowed me to focus on the protocol and also start forming a storage abstraction layer. So once I had this in place as a prototype, I was able to do some benchmarking and make sure that I was still on the right track in terms of how the thing would perform while responding with actual payloads, right? So responding with a Pong, that's only a handful of bytes to respond. But with a cache, we might have items that are much larger that we're responding with. So I wanted to make sure that all the buffering and parsing and response composition was all really good. So I did some benchmarks, and those were looking promising. So we can move on at this point to adding FFI wrapper around the C storage library and integrating that into this new implementation. But of course, I'd run into some issues at this point. Choosing to use Rust versions of some of the foundational libraries left me stuck in terms of trying to use a storage library which had metrics and logging deeply integrated into it. And we wanted that. We need really good insight into the performance and be able to debug things. So I had a choice at this point. I could either rip out the Rust versions of these libraries and improve the ergonomics of the existing wrappers for the C implementations, or I could maybe figure out some way to make the C library, the C storage library, talk to the Rust implementations of metrics and logging. It really got super gross super fast, and I probably spent way too much time feeling just absolutely crushed by this problem and trying to figure out some way to move forward. Ideas that seemed bad were starting to sound better. Maybe I could rewrite this storage library in Rust. And there were a lot of reasons why I didn't want to do this. The storage library essentially winds up being this place where we run into all sorts of things that aren't super easy to do with Rust. We have self-referential data structures and managing memory allocations to avoid external fragmentation. We've got many linked lists, pointers all over the place, unsafe code everywhere. It just didn't seem like the right thing to do. On the other hand, maybe we could simplify things a little bit. Maybe if we start with something that's only single-threaded, that we don't need to think about concurrent access, that might make it a little easier. Maybe we could just implement the hash table in Rust and use C code to allocate and manage these big blocks of memory. All this wound up being depressingly difficult as well. Luckily, around this time, there was a newer research storage design by a PhD student who was working with us, and this new design was a lot easier to port to Rust. I even simplified that design further and took it back to being designed for single-threaded use, so there's no locking or concurrency things that I might get wrong. Rust does make these things pretty easy normally, but for memory efficiency reasons, I wouldn't have been able to use the Rust primitives for doing locking and concurrency. They use too much memory for this particular use case. But best of all, once I went down this path, I found I was able to manage all the memory from Rust and not have to deal with anything terribly exotic like a custom allocator or anything to make this work. So it was actually pretty straightforward once I started with a different style of storage library. So there were downsides to doing a rewrite, and these would apply to whether I did this rewrite into Rust or C or any other language. It cost me 2 months of work that was essentially duplicating previous efforts. And even at the end of that, I didn't hit exact feature parity. There's more work that needs to be done still. In terms of benefits, though, this kind of caused us to move forward to using this newer storage design, which has benefits for a lot of our workloads at Twitter. Otherwise, we still would have been on that older storage library and not even been able to start tapping into some of these benefits of the new design yet. So this kind of forced us to move forward a little bit. Additionally, during the rewrite, I identified some areas where we could improve this new design even further. And these improvements would help some percentage of our workloads. Not all of them, but enough that this also seemed like a win. And lastly, it helped make it more production ready. It was pretty much a research/reference implementation of a storage library, and having another software engineer come through and take that code and really dig into it helped address some of the things that might have caused us some pain a little bit later. So it's always good to evaluate this kind of stuff and see if there are tweaks you can make to improve things further, or areas where you can clean up and have a second set of eyes really deep into the code. There were benefits purely that came from rewriting this in Rust instead of picking any other language. And really, I've seen this quote before on the RustLang page, but it rang extra true after working on this project. Rust does empower everyone to build reliable and efficient software. The code you produce winds up being high performance, and you're able to code with confidence in reliability. The language has all these awesome features and tools around it, and those really help you write good, solid code. Additionally, zero-cost abstraction winds up making you able to express these things in ways that you might not be able to in other languages. So that's really cool. At the end of the project, my manager, Yao, who's the primary maintainer for Pelican, had this quote to say about the rewrite and the benefits of Rust. Yao said, "The Rust implementation finally made Pelican modules what they ought to be, but couldn't before, due to limitations of the C language. This feels exactly right and is just as fast." I think that's really cool coming from someone who is really good at C and has been working in this field for a long time. It's really encouraging to hear that Rust can express some of these things in a way that's a little more elegant and fits better for the particulars of the software. I thought this was really nice. This made me feel good about what I did. As I mentioned before, Rust has awesome tools. Some of the tools that really helped me out a lot in making sure that my code was performant and solid were Cargo Bench with Criterion, doing micro benchmarking of critical components like parsing and the storage library itself and how the hash table works and all these really low-level things. Being able to have micro benchmarks for those critical components really helped me make sure that each of these was very efficient, and that as I started making more changes, I wasn't going to have a performance regression. Additionally, I used cargo fuzz a lot for the protocol library. I wanted to make sure that through using fuzz testing, I was able to find some edge cases that I hadn't quite considered in terms of malformed requests. So that's one of the really great things about fuzz testing is you don't need to think of all these edge cases yourself. You can have the computer start to discover them for you. And when you find something that breaks your code, you can add a new unit test for it. And this really helped me feel like the protocol was going to be rock solid and that I wasn't going to have any weird like crashes in production for having like array indexes be flipped around or all sorts of other things that I encountered while I was fuzz testing. So these two things helped me feel a lot better about the code that I was writing. Here I'm showing basically the benefit of the zero cost abstraction and the traits and type system of Rust and generics really. So here what I'm showing is that segcache, which is the resulting cache server, is a combination of the memcache protocol with this segment-based storage. And we're able to use about 200 lines of code that's a lot of boilerplate, initializing data structures and the runtime and all that stuff. But really, the code between the ping server and segcache are very similar, except they differ in terms of what storage engine they use and what protocol they use. So here we're showing the composability of these things and how we're able to neatly express that with traits and generics. So that's I thought this was pretty neat at the end. And when we write a new storage library or additional protocols, they'll be just as easy to compose together. Some more testing to show off the end results. Here I'm comparing upstream memcache in blue with the Rust implementation of Pelican segcache in red. And I'm going to zoom in on the end of this graph here. At the higher throughputs, we can so it's neat to see that we can actually meet or exceed that performance with a Rust implementation. So just to sort of wrap up some things with a summary. There's more work to be done. There are two parallel tracks that are going to happen at this point. One is the path to production for this Rust implementation. It needs to get to feature complete. There are still a few odds and ends that we need to do in order to have full feature parity with the C implementation. Once that's done, we'll move on to more testing, deploy a single instance out to production as a canary, and then eventually do an actual deployment. And we think we should be able to do this probably by around the end of the year in terms of having a Rust cache server start serving production traffic, and that's exciting. There's future work to do. Earlier, when comparing with upstream memcache, I was showing single-threaded performance, but this implementation also has a multi-threaded configuration, and so does upstream memcache. And while this Rust version of segcache has better performance than our internal memcache fork, especially when TLS is enabled, it loses out to upstream memcache in multi-threaded configurations. I think we can close this gap. The performance is good enough for us to deploy to production, but I still want to win some benchmarks. That's always fun. There's additional optimization that we can do probably even for the single-threaded implementation. There are areas that I want to clean up there. Additionally, this work doesn't get us a Redis replacement yet, and that's still one of the things that we want to do. And we'll go back, we'll figure out what the storage needs to look like for that, need to write a protocol implementation, but we'll be able to reuse all the other components that we have in terms of foundational libraries. And And we feel confident that we'll be able to write a Redis replacement for Pelican in Rust. And then there's all sorts of really cool stuff that I want to play with in terms of this. There's IOU ring, there's like user space TCP stacks. There's all sorts of really fun things that we might be able to do to get even more performance out of this. Rewriting has costs and benefits. The extra time could have caused missed deadlines if I was working towards a deadline. Luckily, I wasn't for this. But I was duplicating work that had already been paid for, so that did have a cost. There were benefits, though. The code was easier to work with once it was all Rust. I didn't have to fight with CMake and Cargo together. And some new ideas got added to the code, so that's probably a win overall. C and Rust are both very fast. Profiling and benchmarking helped me get the performance to match that of the C implementation, but it did take work. The Rust ecosystem has all these awesome tools that I mentioned before. We have Cargo, we have fuzzers and benchmarks and things that help me feel that the code is solid and going to perform well. And then we have tools like Rust Format and Clippy, which helped me make sure that the formatting and that the code was idiomatic, and that went a long way to making the code easier to work with and for my manager to review. And I think Pelican has a really exciting future with Rust. It seems like we'll be able to migrate the whole code base to Rust, and I think there's lots of fun work to come. Thanks for listening to my talk, and thanks to all the folks involved in putting together this conference. Feel free to reach out to me with any questions. Bye.
Hello, I'm Amini Dantras from Huawei's Trusted Programming Group. Huawei is investing in Rust because we believe that it is the best way to produce safe and performant software. I'd like to introduce some of the people at Huawei who are working on improving the Rust language. I lead the Rust Inline Assembly project group, and I'm a member of the Rust library team. I also maintain several crates used by the compiler or standard library, such as Hashbrown, Parking Lot, and compiler build-ins. Guillaume Gomez is the lead maintainer of RustDoc and also a member of the DevTools and Docs.rs teams. They are also a maintainer of the GTK bindings for Rust. Vadim Petrochenkov is a long-standing member of the compiler team and has worked on many areas of the compiler, including parsing, macro expansion, name resolution, the module and privacy system, and linking. Yuki Okushi is a member of the community and crates.io teams, and is involved in triage and prioritization of issues and pull requests. They also maintain the Rust language reference and the Rusty development guide. Finally, Li Yuan and Chen Shuo have both contributed towards improving support for ARM systems in the standard library. We are all looking forward to working with you on improving the Rust language. Enjoy the conference.
Are you too online? Well, our next speaker sure was, and they decided to use Rust to solve that problem. Please help me welcome our next speaker to the stream, Luke.
All right, so I'm Luke, and I'm a relative newcomer to the Rust community. I've been using Rust for about a year. I'm coming to you from the Elm community, where there's a lot of conceptual overlap between the type systems and what have you, but there's also a lot of stuff that's really different. And so I'm really enjoying learning and using Rust. I'm happy to be here. And today, I want to tell you about how I used Rust to become extremely offline. If you aren't familiar with the term, it's a reference to being extremely online, which is a jokey expression for when you spend so much of your time and energy on the internet that it becomes a self-consciously important part of your life. And so what I've been trying to do is sort of the opposite of that, where I'm only using the internet when I need to in more of like a utilitarian fashion. So of course for work and for things like watching TV or finding guitar tabs or, messaging family and friends, that kind of thing. And so the logical next question here would be, why would you want to do that? Especially with the pandemic, more and more of life is moving onto the internet. And why would you want to back away from that in that way? And I will tell you. So around 2017, I had reached a point with my internet usage habits where I was no longer just distracted by browsing. I was spending too much time and investing too much emotionally in what I encountered online. And it transitioned from just merely a distraction to a serious and potent source of anxiety. And my internet habits were not just affecting me at this point, they were also impacting the people that I love and my responsibility to them. And so with very patient help from friends and family, I confronted the situation and decided the best thing for me to do would be to log off and leave it all behind to the extent that I possibly could. So step one of this journey was the classic deleting social media accounts. And I don't actually have a lot to say about that. I'm glad that I did it and that I had the option to do it. I don't really miss it. But it turned out to just be kind of a surface level fix. It wasn't really the posting and the follower accounts that was getting to me. It was a much more pernicious underlying habit that you can pick up while you use social media, and that is doom scrolling, right? It means scrolling through doom. It's the thing where you kind of endlessly swipe through your timeline and kind of inundate your brain with, the day's evidence of humanity's real capacity for cruelty. And it feels awful to do. But for some reason, it's also really addictive. And breaking this habit has taken a lot of time and a lot of energy and a lot of creativity. And I'll tell you how I went about it. So I had deleted my social media accounts, but all of the timelines that I scrolled through are still public. So I had to, in order to cut that off, I had to take kind of a drastic step, and I got a site blocker. Right, the one I chose is called Cold Turkey, and it's a very good piece of software. I highly recommend it if you're interested in that kind of thing. And the creator is really nice about answering my emails. And how it works is it blocks URLs by pattern using a browser extension. And then it's got anti-circumvention features where if you try to disable it or uninstall it, a separate process detects that and will close the browser to annoy you into not doing that anymore. And so I used Cold Turkey to block social media timelines, and then over the course of a couple of years, one by one, I went and I blocked all of the news outlets that were producing these doom-filled headlines in the first place. And so now, as of this year, I built up a fairly comprehensive ban list in Cold Turkey that blocks all of the news sites that I've come across that I would really care to browse. And it's good progress, and I'm really proud of the point that I was able to reach with that approach. But it left one problem still on the table, and that's the search engine. Okay, so I'm a programmer, and I have to use a search engine for work. I have to use a search engine to do anything useful. And so I'll come over here, And, I'll search for some info on the problem that I'm working on, look for some docs, and I'll get some results. But I'm always tempted to come back to the search bar and maybe search for some doom-laden topic. And search engines now, they recognize when you've typed in something news relevant, and they'll show you this like interstitial content within the results, latest headlines or popular social media posts or related videos or what have you. And this little list of headlines here, even though the sites underneath them are blocked in all likelihood, or are of no interest, I still find that just seeing the headlines is actually enough to get into this loop of negative feedback where I'm typing in the news and I'm getting anxious at the headlines, and then I go back up and I type in climate change and I get even more anxious, and it goes on like that until the whole day is over and I'm sitting here just like shaking with rage and anxiety, and I'm in a terrible mood and I got nothing done. But cold turkey can't help here as of the current version because it only blocks URLs and not content within a page that you still want to access. All right, so what do we do? What do I do here? Well, I'm a programmer, and recently I'm a web programmer, so I know how to build a browser extension that can take care of this. And actually, it doesn't take much. Right, so we've got a few lines of JavaScript here, and we'll take the document and search for the distracting content on the page using a CSS selector, and then for each element, just hide it. Simple as that. And we take that and we put it inside of a mutation observer, which is a web API that invokes a callback whenever content on the page changes. Right, so that covers the initial page load, and it also takes care of subsequent updates in a single page app kind of scenario. And it totally works, right? We'll come over here and enable the extension and come back to the search page, and we'll search for the news again, and we'll see that the content is no longer visible. And that's good, that's great. But if it's that easy to go up there and search for a distracting topic, it's just as easy to quickly go over to the corner and remove the extension if the temptation is strong enough, right? So it doesn't really work if you can just turn it off. Some argue that the same is true of type systems. I don't want to get involved in that discussion too much. Okay, so we need what we need to do is implement the same anti-circumvention features that cold turkey has, and we're going to do it with Rust. All right, so here's what we need to build. Okay, so we've got the extension JavaScript running in the browser, and browser extension APIs have this feature called a native messaging host that lets JavaScript communicate with a pre-installed native binary over standard I/O. And the browser starts that native binary in a subprocess and manages its lifecycle along with the extension. All right, so that allows us to communicate directly with the extension through another program. Right, so we're gonna build a daemon that will periodically ask the extension if it's enabled, and if the browser fails to respond through the native messaging hosts, or it responds with something unexpected or incorrect, then the daemon is going to shut down the browser. And again, it'll annoy me into not doing this anymore. All right, so let's check out some of this code here. Let's get into it, starting with the daemon. So this program is trying to decide to do one of two things: close the browser or leave it open. And the first step we need to take is to make sure that we have a PID for the browser, process ID. If we can't find one, that means the browser isn't running, so we can just exit without worrying about it. We don't care. If we do find one, we're going to hold on to it because we'll need it if we have to close the browser later. All right, then we're going to be coordinating a couple of things concurrently, and we're going to use threads, and we're going to use a channel to do that. And channels are good for this because you can clone the sender, you can move it into a closure, you can communicate between threads this way, or maybe not between threads, but you can coordinate what threads are trying to accomplish in this case. So first thing we got to do is set up communication with the native messaging host. Kick off the thread, and then we'll connect to the hosts over IPC, inter-process communication. Then we send a message that just says ping. We're going to wait for a response, and if we get that response back and the response is pong, we're all good. We're going to tell the channel we don't want to close the browser, and if anything else comes back, malformed input or unrecognized input, we're just going to tell the program to go ahead and close the browser. And so at the same time as we're doing that, we're also going to start another thread, and we're going to immediately suspend it for 20 seconds. And in that 20 seconds, if that 20 seconds elapses without a response from the native messaging hosts, we're going to push an outcome onto the channel to close the browser because it's timed out. And we don't think it's ever going to respond. And so now the last thing that we have to do is wait for something to appear on the channel. And once something does, if we're told to close the browser, then we'll use the browser PID that we got earlier to shut it down. And either way, the daemon's work at this point is finished, so we'll exit. All right, so that gives us the daemon. Let's now take a look at the native messaging host side of this. There's not a whole lot going on here. It's just a proxy between the daemon and the browser itself. So what we're going to do is we're going to accept incoming IPC connections. The native message host runs continuously, whereas the daemon will run once and exit. Right? So we're accepting one connection after the next over time. And for each one that comes in, we'll await a request. And if the request is ping, then we're going to move forward and proxy that up to the browser. And then when we receive a response from the browser sometime later, we're going to check it out. We're going to see if it says pong. And if this function here returns true, then we will send pong back to the daemon so that it can finish up. Pretty simple. It's just a proxy. And then finally, we're going to close the circuit here. Right, so the JavaScript side also needs to communicate with the native messaging host. And to do that, we've just got to throw in a couple more lines of JavaScript. So we're going to use the browser's API to connect to the host. We're going to wait for requests. When a request comes in, we first need to ask if the extension is enabled in private browsing. At this point, we know everything else is enabled just because the code is running, but we do have to ask this of the browser at runtime. So if we get an acceptable response there, if everything looks good, we're going to send pong back down to the native messaging host. The native messaging host is going to send it back to the daemon, which will exit uneventfully. And if anything should go wrong in there, if it should take too long, or if the response is incorrect, or any other kind of failure happens, the daemon is going to assume that it happened because I tried to circumvent the system, and it's going to close the browser and annoy me into not doing that. And I'm really pleased to say that this does work, both technically and psychologically, or however you want to put that. It has the intended effect. So if I come over here and the temptation is just so overwhelming, I go and I remove the extension. I can't take it. The daemon's going to execute, and the browser will close. And in reality, the daemon is running once every 10 seconds. I don't have to do it manually, but yes, it works. And I would say at this point that I feel like I've achieved the goal of at least becoming pretty offline, if not extremely so. So yeah, I'm thrilled with this. It was a great opportunity to learn Rust, and I just want to wrap up here first by shouting out some of the crates that I used. So there's psutil for getting the PID, interprocess for IPC, libc for closing the browser, and then serde and byte order for communicating with the extension from the messaging host. And then I want to plug that I work at Struction Site. We're building project tracking tools for the construction industry, and we use a lot of Rust, and we're only going to be using more. Right? We've got a server, we've got processing jobs, and now we've even got front-end code that we've built with Rust and compiled to WebAssembly. And we've also used Elm for our user interfaces. So if any of that sounds interesting, you can head to instructionsite.com/careers and check out the positions we've got open. And feel free to reach out to me as well. And then lastly, here are some places that you can reach me. Feel free to send me an email, or you can find me on GitHub. And if you like to play chess, you can find me at chess.com. So thank you so much. I'm really honored to be able to speak at RustConf this year, and I hope you enjoyed this.
At AWS, we believe leaders create more than they consume and always leave things better than they found them. The two features of Rust that we believe are most important are security and sustainability. The memory and concurrency safety of Rust make it possible for AWS engineers to build great customer experiences quickly and safely. And Rust's low resource requirements make it possible for AWS engineers to build more sustainable solutions. Rust has quickly become critical to building infrastructure at scale at AWS. Firecracker, Amazon's first notable product built with Rust, launched publicly in 2018. We use Rust to deliver services such as Amazon Simple Storage Service, Amazon Elastic Compute Cloud, Amazon CloudFront, and more. AWS didn't start Rust or make it the success that it is today, but we'd like to contribute to its future successes. AWS has been a proud sponsor of the Rust project since 2019, and in 2020, we started hiring Rust maintainers and contributors. AWS is excited to partner with the Rust project to build secure and sustainable solutions. Together, we can create technology and community that outlast us all.
Our next speaker is here to tell us about attributes that you should be using in your code, along with a special message for Steve. Please help me welcome to the stream, Jackson.
Hi folks, and thank you for listening in. My name is Jackson Lewis, and today I want to talk about cool ways to use Rust attributes that you might not have heard of before. I'm going to assume that you have an intermediate understanding of Rust for this talk, because today is going to be a deep dive into some of the more obscure aspects of the language. That being said, I've done my best to make this accessible to everyone. Let's get right into it, shall we? So, as Albert Einstein once said, Rust attributes are pretty lit. I agree completely with Dr. Einstein. As the man who conceptualized space-time, he would surely understand that part of being a programmer is acting like a time traveler. You must protect your code from your future self, who will forget all the nuanced details of what you wrote and ruin everything. Luckily, we Rustaceans have tools to help mitigate this issue: code comments, idiomatic guidelines, and strong typing. But in my opinion, the attribute is one of the greatest tools we have as Rust programmers. One that can save on boilerplate, reduce the chances of making mistakes, and boost productivity all at the same time. So, for those of you who don't know, an attribute is like a tag that you can put on a function, struct, or statement that tells the compiler to do something special. If you've ever derived a trait for a struct, then you've used an attribute from the standard library. Or you might have used the test attribute before to write a unit test. But that's not all. You can also define your own attributes and import them from third-party crates. For example, SeerDay is a popular third-party attribute that will automatically derive functions to manage the serialization and deserialization of your structs. You can see it being used here. And there are other popular libraries besides SeerDay, like tracing, async trait, and so on. But I'm not here to talk about those, because those popular libraries are only the tip of the iceberg. If you browse through crates.io, you will find hundreds of attribute libraries that get completely neglected. And even in the standard library, there are attributes that no one seems to use. So today, I want to talk about 5 of these attributes that are hidden in both the standard library and package registry, and how they can give your code superpowers. So to keep this talk interesting, I'll be explaining these attributes through a hypothetical story. Okay. What we have right here is the option enum, one of the most foundational types in Rust. One day, a controversial feature request proposes adding a third variant to the option enum called possible. While the maintainers insist that it's rather redundant, the creator of this feature request says that it will revolutionize the language. But there's a problem. Currently, people can write code that matches on an option like so. We have a branch that matches on the some variant, and a branch that matches on the none variant. This code is an exhaustive match right here, since it matches on all the variants of the enum. However, with the introduction of the new possible variant, this match on option will no longer be exhaustive, and this code will fail to compile. As you can see, exhaustive matches are fragile to changes in enum variants or struct fields. Because of this, crate maintainers can often feel pressure to push a new major version every single time they make modifications to public enums or structs, in the worry that the changes will break downstream crates. But is there a way to prevent this from happening? As a matter of fact, there is. So let's rewind time a bit and go back to our hypothetical story. If the Rust team had planned from the very beginning to expand option in the future, and didn't want to break existing code when they did expand it, what might they have done? The answer is the non-exhaustive attribute. Non-exhaustive tells the compiler that more variants or fields will be added to the enum or struct in the future. So any crate which uses it needs a wildcard when pattern matching, even if they've already matched all the existing variants or fields. It should be noted that adding non-exhaustive to your enum or struct is a breaking change to your API, because it invalidates any match statements that do not have a wildcard branch. So if you want to make your enum or struct non-exhaustive, it's best to do it when you first make it. Okay, let's go back to our code from earlier. If non-exhaustive had been added to the option enum, our pattern matching code wouldn't just look like this. We would need to add this wildcard statement too. Even though we've exhaustively matched all the variants, we need to add that wildcard or the compiler will throw an error, because the wildcard will cover future changes to this enum. As you can see, even after we add the new variant, this code will not break, since the new variant will be covered by the wildcard branch that we added. And that's the power of non-exhaustive. Okay, so shortly after this controversial rewrite, you take a break from open source to work for a local pizza restaurant. They are very forward-thinking, so their website backend has been written entirely in Rust. However, they also have a legacy codebase written in C, which is slowly being replaced with Rust code. They have a function in this Rust code called pizza validator that checks if a customer's pizza order is valid. Unfortunately, it has two major problems. One, it's poorly optimized, and two, it allows customers to order pineapple on their pizza. Gross! However, for one reason or another, the company doesn't want you to make any modifications to the existing function. Instead, they want you to write a new function that will gradually be phased in to replace the old one. So, a short while later, you've written a new and improved pizza validation function that outlaws pineapples, and you've gone around the code for the new site and replaced many of the existing calls to pizza validator with the new function. But there's a problem. A few days later, an order for pineapple pizza comes in, which, shouldn't be happening. You identify the problem in a function called add-to-order. It turns out that someone else recently rewrote this code, and in the process used the old validation function. But to be fair, there was little indication that using it was wrong. So, let's rewind time again. What should have been done here to prevent this? Well, it would be nice if we could mark this old function as being improper to use without outright removing it. And it turns out that the standard library gives us a way to do this. All we need to do is put the deprecated attribute at the top of the function, and the compiler will emit a warning when someone tries to use it. You can even provide a custom message to go with this warning. So now, if we try to use the old pizza validation function in the new function code, we're going to get a warning from the compiler. And in this case, you don't just want a warning. You want to make sure that using a deprecated function will throw an error for certain parts of your codebase. So if you put a deny deprecated attribute here, or at a higher level in the crate, the compiler will make this an error instead of a warning. And that's the power of deprecated. A few days after this incident, a report comes in about the legacy codebase. A segmentation fault is occurring due to a mistake that a programmer made while using an unsafe function called toBox. This legacy codebase has several unsafe functions that require the usage of raw pointers in order to work with the old C library, and toBox is meant to convert these raw pointers back into a safe box pointer. As you can see, whoever wrote this function left safety documentation in the comments, which is the right thing to do. However, there are still two problems with this code. The first problem is that toBox can still be used without the programmer looking at the safety documentation. And the second problem is that this safety documentation fails to mention that passing in a null pointer will also cause a segmentation fault, and it is unsound to pass in a pointer that points to memory which was not allocated by the global Rust allocator. But I can understand that, because when you're running a safety comment, it's possible to accidentally overlook some edge cases. Now, what can we do to fix this? Well, we could start by expanding the safety section and putting a debug assertion to check if the pointer is null. But still, proving that the function is safe is still dependent on the function itself and not on its caller. Wouldn't it be better if the caller was responsible for proving that they're using the function safely? Well, this is where pre comes in. Pre, which is short for precondition, is a very underutilized third-party macro crate that requires assertions to be placed at both the function definition and the call site. First, we need to add the preconditions to the function definition to toBox, as seen here. So in this case, the pointer must not be null, the pointer must be unique and not be shared with another object, and the pointer must point to memory allocated by the global allocator. This, looks very similar to what we wrote in the safety documentation. Okay, now let's go to the code that was segfaulting and see how pre can help programmers avoid mistakes with unsafe functions. So, at a glance, it looks like this code is run when the user wants to create a new pizza with random toppings. As you can see, the code first creates a pizza struct by calling into the legacy C library, which appears to be wrapped with a safe binding on the Rust side, so we don't need to use unsafe here. The pizza struct does have a default method on the Rust side of things, but it looks like we're using a function from C to allocate it for whatever reason. Then it passes the pointer into the randomize function, which will randomize the toppings for the pizza. Though this also calls across the CFFI, it appears to be wrapped here, so we don't need to use unsafe. And then finally, it gets a unique box pointer to the pizza back using toBox. Since toBox is an unsafe function, we need an unsafe block here. However, since we've added preconditions to the toBox function, we also need to assure that we're using this function correctly, or this code will no longer compile. And adding these assurances will help us spot the reason why this code is segfaulting. So first, we need to assure that this pointer won't be null by putting the assure attribute, which is part of the pre-library, on this toBox call. This will run an assertion in debug mode at the call site with the provided condition. In this case, that pizza pointer is not null. Note that we also have to add a reason as to why this precondition is satisfied, which makes users more aware of whether or not the provided condition will hold. As we add in the other assurances along with their reasoning, we catch the problem. toBox is only safe when we're using a pointer which was allocated with the global Rust allocator. So the first line of code, where we allocated the struct from C, was the offender. After we rewrite the code to allocate the pizza on the Rust side, we can provide a proper reason in the assure attribute for why these conditions are satisfied. As you can see, pre is a great way for users of unsafe functions to be cognizant of what needs to hold true for the function to be safe. And that's the power of pre. That being said, I highly recommend that you limit this attribute to functions that you define internally, so downstream users don't need to add pre as a dependency to their crate just to call the function. The next week, you're asked to perform a refactor on the pizza struct. When you go to make some changes to it, the definition looks off. Something about it is seriously bothering you, but you can't place your finger on it. Oh, that's right. It's these publicity modifiers right here. The fields are public so that you can read from them directly instead of using a getter function. That's useful. But any programmer could also modify these fields if they owned this pizza variable mutably. Furthermore, since all the struct fields are public, the struct can be initialized elsewhere using raw struct initialization syntax. And all of this bypasses the existing functions which are meant to handle state changes and initialization of the pizza struct. But the good news is there's an attribute to fix this. It's so useful, in fact, I wish it was in the standard library. It's called read-only. All you have to do is add read-only as a dependency to your crate and then put the read-only make attribute on the struct of your choosing. Any function that would have had access to these fields, even if they were public, can still write to them. For example, this mozzarella method can still write to the struct directly. But outside the file, you can only read from the public fields, and you can't initialize the struct with struct initialization syntax. So this function right here will compile just fine, since we only read from the cheese field, even though we're taking the struct as a mutable reference. However, this function will not work, since we try to modify the field directly, and then we also try to build a new struct using initialization syntax. This will create two separate compile errors. But to solve our particular problem, we don't need to make all the fields read-only. We just need to keep a few fields from being changed. The good news is that read-only supports this too. By putting the read-only attribute on individual fields, the other fields can still be written to based on the normal publicity modifiers. And that's the power of read-only. Okay, finally, there is one major problem that still needs to be resolved with the pizza restaurant's website. The legacy system and the new system use a separate database for storing customer orders. Since the new system should read from both databases, a trait called order has been created, which provides a common interface over the two order formats, which will let the new system deserialize, operate on, and then serialize these two schemas interchangeably. But unfortunately that doesn't work, because Faraday can't serialize and deserialize trait objects, due to object safety rules with the serialize and deserialize traits. As you can see here, if we try to create a box pointer to a dynamic trait object, the compiler will tell us that order is not object safe. And this is because Faraday serialize and deserialize traits are requirements for this trait, and those are not object safe themselves. So let's go back to the order trait, this time with no requirements for serialize or deserialize, because that clearly didn't work as planned. In order to serialize and deserialize an arbitrary object of this, we're going to need the third-party type tag attribute. Type tag lets you serialize a trait object as an enum, where each variant is an implementer of that trait, and the content is the serialized version of that implementer. Here, you can see that we serialize the order trait as a tagged enum using the arguments we pass into the attribute to specify the names of the tagged fields, in this case type and content. And then, as long as each implementation of order implements serialize and deserialize themselves, we can use type tag to make them serializable as trait objects. All we need to do is put the attribute above each implementation, and this works even if the implementations are in different crates, which I think is really cool. Now, the code which previously failed will compile without any problems. And that's the power of type tag. Alright, that just about wraps it up. I've hoped you learned at least a few new attributes and how you can apply them to real-world scenarios. Here is a list of cool attributes that I didn't have the time to talk about. I highly recommend you check them out on your own time. Thank you so much for listening and have a great rest of your RustConf.
Hey folks, this is Anatoly. I'm CEO and co-founder of Solana Labs. So we've seen an explosion of demand for Rust devs who want to jump into the blockchain space. A lot of new modern day blockchains are built in Rust, but we're starting to see a trend of the application language environment to be also Rust focused first and Rust centric. For example, Solana's application environment is a Rust compiler, through LLVM that targets a new backend based on the Berkeley packet filter. The primary language that devs build new financial applications is Rust, and the reason for picking Rust is that the safety guarantees that the compiler provides are often necessary to build secure, high-performance financial applications. Just simply like something like check math saves 1,000 bugs that developers will often write without those libraries present. So we're super grateful for those tools, but we see that this is a growing trend, and because Rust has tremendous usage outside of blockchain, outside of smart contracts, it's actually a great thing as a platform for smart contract applications. You really want to have a pool of developers that are worldwide, that have expertise across different industries, as folks that can jump in and build these applications.
Before we get into our next talk, I want to give a huge thank you to all of our speakers. Of course, the conference couldn't happen without them. Due to the uncertainty of planning around the conference, not knowing whether it would be in person or online, our speakers had to put their talks together on a much more aggressive timeline than normal, under very stressful life circumstances. It wasn't easy, and they all put in a ton of work to make it happen. So thank you all. This conference couldn't happen without you. Now, without further ado, please help me welcome our next speaker, Zach.
A biologist, a physicist, and a Rust programmer are observing a house. Two people go into the house, and a while later, 3 people exit the house. The biologist says they reproduced. The physicist says there was an error in the measurement. And the Rust programmer says there are now -1 persons in the house. 3 people, 3 different sets of assumptions about how the world works. I've been programming for a long time, more than 20 years now. Over that period, I've held several jobs across various unrelated industries with diverse teams and used many programming languages. Each scenario came with its own unique problems, but in every environment, the same issue has come up over and over again. That issue was maintaining consistency in code written by different people and at different times. A well-architected, well-implemented program is internally consistent. There are patterns and design choices that are adhered to in remote locations across the code. When done well, it's a beautiful thing. But if you change or add code, how do you keep consistency with the design choices already made? Let me give you an example of what can go wrong when consistency is not maintained. Here's a fictional game component in a made-up, maximally terse, and permissive language called hazardlang. We have a poison class, which encapsulates game component logic, and an event that damages the entity with each tick of the game loop by subtracting 1 from its health. Can you spot the bug? It's a trick question. The bug can't be seen when looking at this code in isolation. The bug only manifests when this code is used within a system of components that make different sets of assumptions. Let's look at another component that, in practice, would be in another file. Being in another file may make it less likely that you ever see the code side by side. This missile class has an event on collide that damages any entity it collides with. The difference between this component and the previous is that it locks the entity before modifying its state. There's no obvious problem with either the poison or missile component taken individually. Only by looking at both simultaneously can we see that each makes different assumptions about the system they belong to. One locks the entity before modifying its state, and the other does not. Which one is correct? This is another trick question. No component by itself can be either correct or incorrect. The whole program is only correct if every component agrees with the same set of assumptions as every other component. The poison component may assume that the system has 2 copies of the state, one copy for updating, while another thread looks at a read-only copy for rendering. The missile component may assume that the system allows for concurrent entity updates. The larger the program, the more chances there are for inconsistencies. Since any line could create an inconsistency with any other line, the potential for inconsistency grows exponentially as a function of the program's size. This is why large-scale development is difficult. Over the last 20 years, much of my attention has been devoted to cultivating best practices for scaling codebases without creating inconsistency. What did I learn? Cease development, read all 27 million lines of the program and its dependencies. After a month, When you fully understand how each line interacts with every other line, make a small change and hope nobody else touched anything over that time. Repeat until you go out of business. I'm being sarcastic. What are some practical things we do? We write comments. Comments help, but it's not enough. The architecture is spread out all over the code. To explain how every line conforms with the overall design would be redundant, so people don't do that. Worse, if you are writing new code, any relevant comments would be, by definition, somewhere else where you can't see them. You can't have new code agree with the comments if you don't know the comments exist. We gain experience and we share tribal knowledge. It helps, but it's not enough. One way we disseminate lessons learned over time is by communicating best practices. An example of a best practice is no global variables. But nobody agrees on what the best practices should be. The reason nobody agrees is that everything is situational. If you are writing embedded software, global variables may indeed be the best answer to a problem. So best practices are more like ideas to consider because I got into trouble a few times. As such, best practices are not a solution to finding out what constraints apply to the code you are writing right now. The neglected company wiki is not the answer, nor is code review. I could go on, but that's not the point. Here is the point. The more I consider the problem of maintaining consistency, the more I'm convinced that the best return on our investment as a discipline is in the compiler and in compiler-aided solutions. Unlike communication or mentorship, the compiler scales to any team size, giving personalized advice to every contributor exactly when they need it. Unlike a company wiki, the compiler cannot be ignored or out of date. Unlike some random blog post on the internet, the compiler has complete knowledge of your project's source. For the remainder of the time, I want to tell you how Rust's compiler and standard API work together to create a pit of success for compile-time social coordination, starting with the locked entity example. We'll also look at how you can leverage the same features in your libraries to create consistent pits of success of your own. Let's look at how a mutex is used in Rust, preventing the problem we saw with the game components. The first line moves the entity into the mutex. Now, if we try to access the entity data without locking, the whole program fails to compile. The compiler will tell us that the entity cannot be accessed because it has been moved into the mutex. So we roll that back. Only by locking the mutex can we modify the underlying data. Past the second line, the lock is no longer held, and once again, the data in the entity is not accessible. For some of you, this is not new information. Of course, a mutex would own its data in Rust. Of course, you cannot modify data while the lock is not held. But I want for you to rediscover the joy and quiet brilliance of this API. Some people new to Rust may be hearing it for the first time. I'm confident that they didn't hear it before Rust, because this API is impossible in C++, C#, Python, JavaScript, Java, PHP, Haskell, Go, Swift, or any other mainstream language. People coming from these languages may have recently spent time debugging a forgotten call to lock, or they may have recently stored a reference to data protected by the lock to use later on the UI thread. Or maybe they locked the wrong lock, or forgot to release the lock. None of these bugs are possible in Rust. We can go even further. The consistency guarantee afforded by the mutex API allows us to make some wild optimizations that would never get past code review in any other language. There's an innovative API on mutex, getMute, which takes a unique reference to self, returning a wrapper over a unique reference to our data. The comment for getMute says, since this call borrows the mutex mutably, no actual locking needs to take place. The mutable borrow statically guarantees no locks exist. So there is a way to get access to the data in the entity without locking, but it's checked by the compiler. Whoa. Imagine committing some code in another language with a comment stating a lock does not have to be required here because we know that nothing else has access to the data at this point. First, you would not be trusted to make this assertion. Even if your claim were verified, the change would likely be rejected in review because we do not know if the assertion will hold in the future. This is again the same social coordination problem playing out across time. Because the social coordination problem is so hard, we've become accustomed to the habit of engineering suboptimal software to avoid making mistakes. We've even invented entire architectures that are elaborate kitty gloves hiding the important part of the problem we are actually trying to solve, transforming the data. What at first glance appears to be a restriction imposed by the compiler actually grants us the freedom to write better software without being constrained by the limitations of communication and shared knowledge between its authors. Let's look at another example in hazardlang, this time of serialization. Here we have a generic serialization function in hazardlang. It takes a collection of names and values to serialize, zips them together to form a property collection, loops over each property, then writes a tag for each name, followed by a write of the corresponding value to the file. Where's the bug? The theme of this talk is bugs that come about through poor social coordination, bugs that don't fit on one screen. Let's take a look at another file. The scheme used here by Hazard Serializer is to have the index in the schema serve as the tag. There's a comment stating that the schema needs to be consistent. Okay, no bug yet, but our story is not over. Remember this part about the schema needing to be consistent. One day, the original developer leaves, and another developer is hired to replace them. The new developer writes this usage of Hazard Serializer. Maybe they didn't notice the utility function that the original developer wrote, so they do some things by hand. They set up their schema with a predetermined consistent order, just like the docs said to. And they write tagged property names and values, just like they're supposed to. So the new dev tries their usage of Hazard Serializer and writes a file. But when they take a look in the app, the data is all wrong. They ask around and get the story that because there was so much trouble maintaining consistency in the schema between the server and the client, that the convention among the team is to use alphabetical ordering in the schemas. Here it is using name, date for the writer, but the reader, which is implemented somewhere else by someone else, uses date, name. Ugh. The new dev, being the proactive sort and ready to make a good impression, decides to fix this once and for all. The dev makes this commit. The old version is on top and the new version is on the bottom. The dev added a call to names.sort, which ensures that there's a consistent ordering that adheres to the internal convention of having alphabetical names. Their code now works. There's an added benefit that there are fewer requirements for calling this function, so the bug won't be hit in the future. And we ship. Yay! Except nobody looked at these two pieces of code at the same time. The old serialize function that I showed you at the start with the new fixed tag function. Do you know how many things a person can keep in their head at once? 3 to 4. So even in the few minutes I distracted you with a story about the new dev, we may have forgotten to consider how this change would interact with the old code. So what's the problem? Well, if you look at both sections at the same time, you can see that we are iterating over a list while modifying it. Oops. The program probably won't crash. Instead, it will write garbage data, which is arguably worse. At no point in time was this serialize function and the new tag function on the same screen at the same time. People changed different bits, fixing the problems they were aware of, creating local consistencies but global inconsistency. Remember that these examples are simplified. Real codebases are comprised of huge directed graphs of function calls being mutated concurrently by multiple people. Even if two inconsistent nodes in that graph were just a few hops away, there could be hundreds of nodes reachable within the same distance. Finding the inconsistency is much like finding the needle in a haystack if you don't know a priori where to look. Our example may seem contrived, but the issue is common enough that a Google search for the phrase, "don't iterate a list while modifying," comes up with over 50 million results. This time-lapse animation shows only the files and directory structure of a project that I worked on at the Graph to index blockchain data. If the nodes for structs and functions were included here, there would be more than 3,500 more nodes on the screen and uncountably more connections. Yet, this is a modestly sized workspace maintained by a relatively small team. Avoiding iterating over a list while modifying it in hazard lang required social coordination. But it's a mistake that I've never made in Rust, even when working with other people. The compiler ensures for me that the connected nodes in our call graph are consistent. In Rust, there are 3 ways to pass values. You can use a shared reference to T. A shared reference is immutable unless you implement special protections to guard against the problems that come with shared mutability. We call that interior mutability. But the typical shared reference is read-only. There's also unmute T, unique reference to T, which enables the permission to write to the value. And finally T, which transfers ownership of the value. Using these 3 types, we make explicit what are hidden contracts in hazard lang. The Rust compiler can verify these contracts. Let's see how it does that. Our serializer bug boiled down to iterating a list while modifying it. If we try the same in Rust, we get a compiler error. This is the distilled version of the bug. Here at names.iter, a temporary is constructed that maintains the state of the iterator. The iterator holds a shared reference to names. But on the following line, the call to sort takes names by unique reference. It is a contradiction for a reference to be both unique and shared at the same time. Contradictions are bugs. What's neat here is that Rust will detect this contradiction through any number of layers and structs and function calls, so that even if the code is not simple like in the example, it will not compile with the inconsistency. The bug we introduced in the serializer cannot occur in Rust because the whole program would fail to compile. We're almost done. I promised to show you how to use the compiler to enforce your own rules that would otherwise require social coordination. We will use the type system and compiler errors to teach new developers architectural decisions. This is going to be a bit of a doozy, so please prepare yourself by enjoying this picture. Okay, let's go. First, set up the situation. At Edge and Node, we write multi-threaded web servers that each serve thousands of requests every second. These servers read data from a database. The database has a connection limit, and connection takes time to set up. So to avoid going over the limit or incurring the setup cost on every request, we use a connection pool. One day we noticed that a server instance stops serving requests. There's no warning. Everything stops. CPU usage flatlines, there's no disk usage, no queries are served, and if we restart, everything is okay again, until the next time that it happens. Why? Note that at this point, you're looking at an issue that is going to be difficult to debug. It's a real server with lots of code. Customers are panicked, and the issue only occurs once every few days under vast amounts of load. There's no stack trace in the logs or smoking gun of any kind. Here's the bug we found. First, get a connection from the pool. Then, save data using the connection. And lastly, emit an event to notify any listeners that there is new data available. Where's the bug? It's not here. It's in the interaction of this code with other code. Let's look at some more code from a file far, far away. The code in emit event also appears straightforward. Our pub sub goes through the database, so we grab a connection and write an event to it. There's no obvious bug in this code either. The problem is that when emit event is called, we're already holding a connection from the connection pool. The connection held is not returned to the pool until it is dropped after emit event returns. In normal circumstances, this is okay. The second connection is acquired, and then both are released. First, the connection in emit event is released, then the outer connection is released. But rarely, if 50 requests hit emit event simultaneously, they're already holding the limit of 50 connections, so the call to get connection within emit event never returns because the connection pool is empty. Since emit event never returns, none of the outer connections are returned to the pool, and the whole request pipeline is deadlocked across all threads. In order to understand this bug, you have to be aware of very specific architectural details. You have to know that connections are pooled. You have to know that events go through the database. You have to know that connections return to the pool on drop. You have to know everything that those disparate details infer. And you have to know for any function that you are writing that no caller of your function holds a connection if any call you might make would attempt to acquire one. So you have to know all the code up and down the stack at all points and keep all of this in your head on top of thinking about whatever problem you are actually trying to solve. Since interacting with a database happens in many places, there's a large surface area of code susceptible to this bug. At this moment of discovery, experience and tribal knowledge are formed. The developer working on the bug says, "Aha, it is incorrect in the general case to hold on to a pooled resource and ask for another from the same pool. Doing so will always eventually deadlock." They share this information with the team, write a blog post, add a comment to get connection, and go on a conquest to stamp out every instance of this bug they can find. But this bug is really subtle. It's easy to miss, even when you know what to look for, because you have to analyze regions of a directed graph of function calls. You have to look at the scope of the liveness of the connection. In this case, the scope is between getConnection and past the end of emit event. You have to see what function calls overlap with that scope. Then traverse the directed graph of calls until you visit every reachable node and verify that none of those nodes attempts to get a connection. Even if you get it right, someone can make a minor edit in the middle of the graph in the future. This edit may completely change the set of reachable nodes. They may be unaware that upstream a connection is held, while downstream a new connection is obtained, because from where the edit is made, they may see neither. So here's this bug. It's hard to detect, easy to create, is not fixable via architecture, and hurts users in production. It's time for compile time social coordination. What we want to do as leaders is to take our learnings about the resource starvation hazard inherent to pooled resources and encode those learnings in a type system so that the compiler can then teach the rest of the team at scale and at the appropriate time. The rule that we want to enforce to prevent this bug from coming up again is that each request may hold up to one connection, but never more during the scope of the request. The solution is to create a token representing the permission to obtain a connection from the pool. We can ensure this permission is granted once per request by making the token constructor private. GetConnection is then appended to take a unique reference to the token. What that does is to tie the unique loan of the token to the loan of the connection from the pool. The connection is returned to the pool on drop, so only by returning the connection to the pool can we release our loan of the token. What is the effect of this change? Returning to the call site of emit event, we now need to pass our token into get connection. And we need to pass our token into emit event for it to be able to obtain a connection. But now this won't compile because the connection is still alive when we try to borrow the token the second time. The compiler forces us to add this line to return the connection to the pool before calling emit event. This fixes the bug, not just here, but everywhere it might exist in a source now and in the future. That's it. A dozen lines of code to set up the rules, and the graph traversal search for inconsistency is now mechanically executed by the compiler, removing the error-prone and easily forgotten work from the developer. As a bonus, the token is removed at compile time. There's no heap allocation or any runtime cost at all. All of these problems, locking entity data, modifying a list while iterating over it, and resource starvation have two things in common. One is that they happen all the time. The second is that they're all part of a broader class of problems fixed as a natural consequence of the borrow checker. In fact, many other social coordination problems like memory management, if I pass a pointer to your library, whose responsibility is it to free that memory? Safe global variables, high performance non-defensive code, security, even WASM support are all underpinned by the borrow checker. The borrow checker is the beating heart of Rust and is why I use Rust. You could say I use Rust because of its safety, performance, WebAssembly, productivity, excellent tooling, supportive community, its empowerment, etc. All true. But none of these I consider differentiators. They are important, but they are literally the minimum bar. I have no use for any language where I cannot write programs with excellent runtime performance, or which does not compile to the platforms I care about, for example. Among the small set of languages that meets this minimum standard, I ask what sets them apart. For me, it is lifetimes and the borrow checker. Lifetimes have a reputation for being hard to learn. These fears aren't entirely misguided. Learning Rust is hard. It took me longer to learn Rust than any other language. But there's a narrative being perpetuated in our community about the borrow checker being difficult, that people fight the borrow checker. While true from a certain lens, I believe this narrative to be misguided and counterproductive. Do you want to know what was harder than learning lifetimes? Learning the same lessons through 20 years of making preventable mistakes. The whole result is refreshing because there's a single unifying concept that provides a benefit across almost all APIs. The accumulation of many small wins adds up. If you want to know in a sentence what's so important here, is that there's finally a language that both has a string concatenation method and I'm not afraid to use it. At the risk of being hyperbolic, I believe that the borrow checker has rendered obsolete much of the knowledge that I've gained over the past 20 years. And I think we haven't even seen how far this experiment will go. Suppose that the future of programming can shed defensive architectural patterns, endless debugging, passing on best practices and tribal knowledge manually, and learn to love one concept, that of lifetimes. In that case, we will see farther and accomplish more than our predecessors. If you're not yet using Rust, that is the trade-off that I present to you. The choice is now yours. If you liked the idea of solving social coordination at compile time, you may also enjoy solving social coordination through incentive systems, which is one of the things I work on at Edge and Node while using Rust. If that sounds appealing to you, we're hiring Rust developers. You can contact me at that3%@gmail.com for any questions about this talk or what we're building. Thanks.
Our next speaker is the king of the tweeting about bad error messages to having good error messages pipeline. Please help me welcome Esteban.
Hi, I'm Esteban Kuber, a member of the Rust compiler team and of the Rust platform team at AWS. You may also have seen me regularly asking people on Twitter to file tickets for diagnostic bugs. I'm here today to try to convince you that you can contribute to the compiler regardless of your background and provide an introduction about how to go about it. A lot of people have this perception of compilers, that they are black boxes that run on magic and pixie dust, and that to get involved, you need to be unusually technically competent in multiple fields at the same time. There is this idea that only elite programmers can play with compilers. I'm here today as living proof that this is absolutely and fundamentally incorrect. You don't need to know or understand every aspect of a compiler to meaningfully contribute. You don't need to know how optimization passes work to modify the parser. You don't need to know how the parser works to understand how type inference operates. And you don't need to understand how type inference operates to learn how lifetime analysis works. And even though I just used a bunch of jargon just now that may be confusing, opaque, or even intimidating, the concepts behind them are straightforward and you have resources available to learn about them. And we will explore some of them in a minute. You also don't need to be well versed in the art of language design. You just need to want to do it. And if you have, or think you may have, that drive, this talk is an open invitation for you to get involved, and my hope is that you will feel empowered to look under the hood of the tools you use every day. The Rust compiler is a big program, but it's just a program. And in some ways, it is simpler than many things you may have already worked with. It's not a long-running distributed service. It's not a UI application. Essentially, it takes text files, ingests them into a pipeline, and delivers either a running binary or a bunch of error messages that I hope have been helpful, but that's it. Of course, there is nuance and very advanced aspects of the compiler, but the vast majority of it is straightforward and well modularized. My suggestion for you to get started is first to find problems you're interested in that need solving, then to set up your environment, and last to learn how to navigate the codebase and identify what needs to be changed and how to go about doing that. Finding something to do can be easy. You may already know something you want changed because you encounter a bug, like an internal compiler error or bad behavior, or there is a feature you want in the language. For new features, there is an RFC and major change proposal process that requires sign-off by the relevant teams, usually the language team for anything that affects the semantics of how Rust works, or the compiler team when it's changed to some implementation detail, specifically if it's user visible. This helps us organize ourselves and avoid people spending too much time implementing a feature in a certain way when the teams may already have plans in that area. Otherwise, you can check the backlog and look for bugs that have been identified or feature requests and pick the one you want to tackle. You don't need to go through the entire 5,000 plus tickets to find something that will pique your interest. You can refine your search using labels to narrow the results to a pool that best aligns with your interests and/or area of expertise. There are 3 labels in particular that I find useful for newcomer contributors. The first one is eMentor, which groups all tickets that have an expert in the subject matter, who is available to help and guide you through the process, or who has already written mentoring instructions that you can follow as you navigate the compiler codebase. The second label I find helpful is EEasy. It identifies tickets that require minor changes to the compiler. This is a good way to get acquainted to compiler internals because the level of engagement needed is localized and more manageable. Lastly, I encourage you to consider looking at the PLOW label that identifies tickets that don't need an urgent resolution. They are more of would be nice to have changes. Often, those changes are easy and quick fixes that just never seem to get addressed. Paradoxically, that lower level of urgency means that the pressure people feel when taking them on is much more relaxed. You can take your time to get yourself up to speed without the fear that, let's say, a stable release is going to go out with a regression if you don't act quickly. If you're feeling more ambitious, you can look at recently accepted RFCs and their corresponding tracking items. where you may be able to help bring new features to nightly or stabilize existing nightly features. It's common for these kind of features to have a lot of low-hanging fruit, a lot of polish work that isn't necessary to put together a proof of concept, but that is crucial to match the level of quality people should expect from us. These are not the only labels we use for categorization. We have prioritization labels, labels to mark what team should be concerned with a given ticket, and labels marking what part of the compiler or feature the ticket is concerned with. We take pride in having a relatively well-groomed backlog, so finding the right thing should be easy. And this is an area where people can help, beyond just writing code. Writing documentation and maintaining backlog are good, well-appreciated contributions. Once you have identified what you want to work on, we need to set up your environment. Ideally, we would all have access to really powerful hardware, excellent Wi-Fi, and unlimited amount of cookies. As you may know, building Rust C requires a lot of RAM. You really want to avoid swapping. You need several dozen gigabytes of disk available and the fastest CPU you can get your hands on. The reality is that not all of us have access to that. Thankfully, the project is currently in the process of procuring cloud desktops for compiler development, to which contributors at large should have access. Stay tuned for further announcements in this area. Now, the feedback loop of writing a change, compiling, and running some tests to verify your changes had the intended effect can easily take longer than 15 minutes on accessible hardware. It's unquestionable that compiling is a time-consuming exercise that can be tiresome. Some strategies to tackle this include making a pot of tea, spending time on Twitter, taking bathroom breaks, or multitasking. Because of this, there is one gatekeeping attribute to thrive when contributing to the compiler. You need patience. Depending on your operative system, your setup will be more or less involved. The first thing you need is getting Git working, cloning the compiler repo in your environment of choice, and have CMake and Python installed. X.py is the main access point to working in the compiler. It lets you orchestrate the build of processes, run different types of tests, and auto-format the codebase. It's pretty much equivalent to Cargo, but exclusively for the compiler. The first time you do this is probably a good time to put the kettle on. The next thing to do is to set yourself up for testing with ad hoc files. I would encourage you to use RustApp to link the compiler you just made as a new toolchain accessible elsewhere in your system. That way, you can write rustc plus dev anywhere in your machine, and it will use your compiler. The same will work for Cargo, which makes it very handy when testing problems that only appear in larger crates or when testing problems for which you haven't found a minimal reproduction case yet. You will also want to get Rust Analyzer working on your editor of choice. A lot of us have slowly gravitated towards VS Code, which will likely be the easiest environment to set up. In order to use a debugger on your compiler, you will need to enable debug symbols, and depending on your operative system, you may have to enable a few other things too. There is a single config.toml file that lets you configure all of this. Fair warning, we are still having some issues with debugger support when working on the compiler due to a combination of some macro trickery we do and gaps in our debug info. In some cases, advancing step by step, you end up going through low-level binary code. Inspecting values can be hit or miss, particularly for enums, complex entities, or variables that have been completely optimized out. Because of that, a common approach is to rely more heavily on debug output, where you pepper your code with debug and info macro calls, and then invoke the compiler with a rustc log flag set to the module and verbosity level you care about. Let's say you've done all of these things, you should be ready to code. Now, let's figure out how to actually go about finding where to make the changes. To help you figure out which part of the compiler you need to work on, I'd like to point to 3 main resources that I highly encourage you to tap. The rustc dev guide, which provides much detail on a lot of the compiler internals and expands on what the workflow can look like. The guide has a lot of useful information, which I try to avoid repeating here, but it is really important to be aware of it. Seriously, if you want to start playing on the compiler's codebase, the best thing you can do is to keep a tab with the guide open. Secondly, you have the Rust-Lang Tulip chat. It's where you can reach out for help to more experienced contributors. And trust me when I say that we are more than happy to guide you through your exploration of the compiler internals. You can use git blame to identify people who have already worked in the modules you're looking at. And you can also use the expert map, which is a hand-curated list of experts for the different high-level modules. And finally, you can also look at merged pull requests and closed tickets. They are a good source of context when working on something similar to existing features. Once you have everything set up and start trying things out, it is important to get acquainted with some of the concepts encoded in the language and how Rust code ends up being represented for evaluation. One thread I like to pull on to untangle the sweater that is the compiler is to look at error messages. It gives you something to grep for, or you can use the flag treat error as bug, which is nightly only, to get the exact place where it is being emitted and slowly work your way backwards from there. A compiler first takes a text file, tokenizes it, which means that it splits the text into small pieces that have some meaning. This is when an identifier is separated from parentheses, or when a string or comments are identified. The parser takes those, one at a time, and based on what it has seen so far, decides what the next element should be. This way, the parser starts building an abstract syntax tree. ASTs are a way of representing code in a way that is easy to evaluate. Once we have an AST, we transform it into another very similar looking tree in the high-level intermediate representation, or here. This tree has extra information in it that makes it easier to evaluate correctness and reference other parts of the code. You may already know about expressions. It's the smallest useful unit you will find inside functions. If you have 1 plus 1, that's 3 expressions, a binary operation expression which owns 2 literal expressions for the numbers. Everything you write inside of a function ends up in a tree of these. But we also have a bunch of other constructs. We have items, which are all of the things that can live inside of a file, like types, functions, and constants, amongst others. These two are the fundamental building blocks of all the code we write, and if you're changing code in Rust C, you'll be interacting with them extensively. Luckily, they hold a very straightforward relationship with the code they represent, so if you already know Rust, you will easily figure out what is that. Once the here tree is populated, the compiler can start doing its other passes. It can do name resolution, where it figures out what each identifier in the code actually corresponds to. It's when we figure out imports and that vec is a type and vec is a macro. It does type checking, which is making sure that you really don't use a signed 32-bit integer when accessing an index in a vector. It does trait resolution, which means figuring out what traits a given type implements and what trait a method call corresponds to. This also has to account for trait bounds, which has its own very complex level of evaluation. For trait bounds and associated types, Rust C models both as obligations, which need to be satisfied. The compiler also needs to do lifetime analysis, where it uses the lifetime that appear in item signatures to verify ahead of time that all of the borrows in the item can be invalidated. The lifetimes only exist to confirm that everything inside of the item, usually a function, is correct, and that it can be called with the bindings you are calling it with. We have a generic borrow checker error that tells you what all of the lifetimes involved are and try to point at everything that may have caused an issue. But we also have a prior check, where we look at the current environment and pattern match against a bunch of known cases. If any of those cases match, then we can provide a more targeted error. And those are the ones that you normally see. If you can come up with cases where the general error is being displayed, adding a case to handle your special case wouldn't be that hard to do. We just need to figure out how to detect it. After all of these are other things that the compiler does, like LLVM intermediate representation code generation, invoking linkers, storing intermediate metadata from the previous steps for incremental compilation. All of those steps are aided by an on-demand query system. A bunch of macros that allow us to avoid recalculating things we've done already by caching them on demand. All of these parts are fractally complex. You can deep dive into a specific part of a single compiler pass and have enough things to do to last a lifetime. But doing useful and fun things don't require digging that deep. When I started contributing was because there was one error that annoyed me, and here I am 6 years later still contributing to the compiler. Once you pull the curtain and realize you can change things, well, it's hard to stop. Now, 15 minutes aren't enough to show the whole development process, and working on big Rust code bases like the compiler is time consuming. but it is also a very rewarding experience. It is a great way of learning how a tool we all use works. It lets you improve it whenever you want. And it lets you pull back some of the artifacts of language design to have a more accurate understanding of how the language actually works. So, if what you saw made you think, this isn't that hard, and have the time to jump in, please do. Remember, you're not alone. We are all looking forward to helping you make your mark on the project. Thank you for your time. Enjoy the rest of RustConf.
Hey folks, this is Anatoly. I am co-founder and CEO of Solana Labs. We're really proud to be a sponsor of RustConf. It's been an amazing tool that helped us build a high-performance, low-latency blockchain over the last 3.5 years. None of us really were Rust devs before we started, and without Rust, I don't think we would have gotten here because of the high performance and the safety that the compiler provides. It's just been kind of our secret weapon when building applications. So we want to thank this community and we want to see it grow. And if you're a Rust dev that is interested in building high performance systems, software, or building financial applications or experimenting with blockchain, please check out Solana.com. So you should find job postings from us or from our ecosystem projects that are building smart contract applications. Or in the hackathon, teams are forming right now. So if you want to just see what it's like and participate and see if you can win a prize, just jump right in. We have a really friendly community. Everyone loves Rust, and we'd love to be a bigger part of the Rust community in general. So thank you so much.
Are we all still awake? Come on, wake up. We got one talk left. Our closing keynote speaker has an amazing talk lined up for you. Please help me welcome to the stream, Nell.
Hello, everyone. I know, depending on where you are in the world, it's either very late or very early for some of you. Thank you so much for staying to the end of RustConf. I'm Nell Shamrell-Harrington. I'm a principal engineer at Microsoft and also a board member of the Rust Foundation. I am the lead editor of This Week in Rust, and if you'd like to get in touch with me, the best way to do that is through my Twitter handle, @NellShamrell. Some of you who attended RustConf last year might recognize me from being the master of ceremonies for RustConf 2020. As you might remember, my 3 pet bunnies, Noah, Lucy, and Leia, all made appearances. They are all well and send their regards to the entire Rustation community. I found Rust through working on the Habitat project at Chef. When I learned Rust, This Week in Rust was a major help and a major inspiration. It was a gateway to the Rust community, a community where empathy and personal maturity are as important as, if not more important than, technical excellence. This Week in Rust, also known as TWIR, is a weekly newsletter that highlights all that is going on in the Rust community. Who watching this subscribes to This Week in Rust? If you do, please put a +1 in the Discord chat right now. All right, who watching has contributed to This Week in Rust? If you have, please put a +1 in that Discord chat. Well, even though I'm pre-recording this, I have no doubt a huge number of +1s just scrolled by. This highlights that This Week in Rust is not just one person's project. I may be lead editor, but I am certainly not the only editor. The current editors are myself, Andre Bogus, and Colton Donnelly. We spend a lot of time and energy making sure that This Week in Rust lands in your inbox every single week. But this newsletter is not only the editor's project. Every week, we receive pull requests adding content, or people tweet at us at @ThisWeekInRust suggesting content. This Week in Rust is a community project. It's created for and by the outstanding Rustation community. This means This Week in Rust is your project. No matter how long you've been interested in Rust, no matter what your level, no matter who you are, your contributions are welcomed and valued. It's your newsletter. It's our newsletter. And its success is because of every one of us. To understand how that success came about, let's start with a look at the history of the newsletter. And like many things in the Rust ecosystem, it started with a conversation on GitHub. Brian Anderson, an early Rust contributor, knew that there was lots of interesting activity happening on the project, but it was too much for most people to keep up with. Ember Arlinks, Brian's intern at the time, took the project and published issue number 1 on June 7th, 2013. This was around the time of Rust 0.7. Can everyone watching this, everyone in the Discord conference chat, please give 3 cheers for Ember right now? As I prepared this talk, I really enjoyed going back through old issues of This Week in Rust. Some highlights include how the older issues would go through each change to the language in words, something that was so helpful in its early days, but would be impossible today. Earlier issues also included lists of new contributors. I particularly like this quote from issue 22. At 0.85 new contributors a day, we'll soon dwarf every other language in the awesome volunteer category. Well, I don't know about you, but I think this prediction definitely came true. Rust is the leader in the awesome volunteer category. If you agree, go ahead and put a +1 in the conference chat right now. Something I also love about the early issues is that they could list all the known uses of Rust in production, something we probably wouldn't be able to do today. I'd like to give a shout out to Tilde and OpenDNS, 2 of Rust's early adopters. Additionally, This Week in Rust used to feature sections about specific projects, including This Week in Servo, which was contributed by Lars Bergstrom. Servo was another of the very early projects written in Rust. Also, This Week in Rust used to feature This Week in Cargo, the Rust dependency manager we all know and love. I learned something interesting when I looked back at the issue where Cargo was introduced. If you've ever wondered why Cargo's website URL is crates.io, it's because a startup was already using cargo.io at that time. Now you know. From its early days, This Week in Rust showed the heartbeat of the growing Rust community, something I believe it still does today. Reddit user Programmer put it this way: This Week in Rust plays a very important role in the Rust community as an aggregator of community updates. I became lead editor of This Week in Rust in early 2020. However, Vikrant Chaudhary, also known as NASA42, was lead editor for most of the newsletter's life. Brian Anderson, another early editor of the newsletter, puts it this way: there were a number of times in Rust history where a volunteer stepped up out of nowhere and just carried a whole subsystem. NASA42 taking over This Week in Rust was one of those. Can everyone in chat please give 3 cheers for Vikrant, also known as NASA42, right now? Thanks to Vikrant's efforts and the efforts of all editors over the years, this year we published issue 400 of This Week in Rust. This felt great, knowing the newsletter has had such a long life. It inspired me to think about the larger context for it in our community. And as I went through the back issues and asked for thoughts from others, 5 key insights stood out to me about the Rust community. Insight number 1, Rustaceans are deeply dedicated to learning and teaching. And this is most apparent in the tutorials and blog posts feature in This Week in Rust. To quote Quindot on Discourse, in the beginning, the articles and blog posts were the most important for seeing new patterns and examples and just learning about Rust generally. When I first started with Rust a few years ago, this section was the most important to me as well. Initially, a lot of the articles were over my head, but the ones which explain key concepts of Rust, things like ownership, borrowing, and lifetimes, were enormously helpful. They gave me the foundation to understand the more advanced Rust topics and practices. Unlike other online communities, I've never been called a noob when I've asked a question about Rust. We Rustaceans don't force people to go through pain in order to prove themselves worthy of being in our community. If you are interested in Rust, you are a Rustacean, you belong here, and we will be with you every step of the way. The absolute best thing about editing This Week in Rust has been to see how dedicated our community is to teaching. We were all new to Rust at some point and are committed to paving the way for those who come after us. Even though I now have a decent experience with Rust, the blog posts and tutorials are still very important to me every single week. Even if a post is explaining a concept I already know, seeing it explained in a different way deepens my knowledge and shows me other ways I can explain that concept to someone else. You don't fully know something until you can teach it. Writing up a tutorial or a blog post about a Rust concept, it doesn't only help your readers, it helps you become a better Rust developer as well. If you ever find yourself wanting to write something up but hesitate because you think, well, doesn't everyone already know this? Please write it up anyway. I guarantee there is someone out there who needs to hear your way of explaining to understand the topic better for themselves. As I learned more about developing Rust, I became more interested in how the Rust language itself is developed. And that leads me to insight number 2, and this was a bit of a surprise. Rust is developed in the open by regular people. If you look at the updates from Rust core section of This Week in Rust, you will see that an astonishing number of pull requests are merged each week. These aren't just major features. They are also small contributions like refactoring that make the compiler better for everyone. As M. Brubick on the Discourse forums shares, I also love that This Week in Rust is a place that gives public recognition to contributions that might otherwise go unnoticed. In the Rust ecosystem, every contribution is important and vital to the success of all of us. As I delved more into the core update section and read through the changes, I got a better sense of not only how the language is constructed, but also a sense of the key people who make it. As Quindot on the Discourse forums put it, but perhaps more importantly, I became familiar with many key Rust developers and their roles and started following their blogs and so on. I personally experienced the exact same thing. When I started hacking on the compiler myself, I found Nico and Boat's blog posts about Rust async functionality, and it really helped me. Because I knew where to find them online, and because they had written down their thoughts, I was able to harness and build upon their recorded experience. This reinforced that I wanted to be more involved with not just using the Rust language, but also creating it. And this leads to insight number 3. Everyone is welcome and encouraged to become involved with the Rust ecosystem. When I was learning Rust, I found I learned about 20% of what I needed to know through things like books and tutorials. This was necessary stuff to learn, and the books and tutorials were fantastic. They gave me a great foundation to build on. But in order to unlock the other 80%, I needed to learn through doing, through writing Rust in real-world projects. One of the best places to find projects to get involved in is through the CFP, or Call for Participation section of This Week in Rust. This section features issues where, more often than not, a mentor is available to help. Moreover, because you know the projects are actively looking for new contributors, you know you will have support as you learn by doing. Another great place to find Rust projects to contribute to is through the Project Update section. Project updates serve 2 purposes. 1, introducing cool projects that people might want to use, and 2, also introducing projects that people may wish to contribute to. It's a great way to get started with writing Rust for real-world projects. As I became more experienced with using Rust, I started becoming more interested in how Rust itself is built. The best way I found to begin to understand this was through reading the RFC, or Request for Comment, and FCP, or Final Comment Period sections of This Week in Rust. These RFCs did seem over my head at first, but what was helpful was focusing more on the comments on the RFCs rather than just the RFC text itself. One of the reasons we have the RFC process is because Rust is used in so many different contexts. It's impossible for any one or two people, or even a few more people, to have all that context in their minds. In order to understand how a change will affect users, we need the context and experience of the entire community. Now, I'll admit, I was initially hesitant to write comments on RFCs myself because I was afraid that people would tell me I was wrong. But, as Aaron Turon put it in a blog post, no one can be wrong about their own lived experience. Rust needs your experience and your comments on RFCs and FCPs to make Rust the best language that it can be. And Nethercoat summed this up nicely on Reddit. This Week in Rust doesn't just distribute information, it potentially draws people into contribution. And once people are contributing, one of the best ways to encourage them to stay is through highlighting their work. And this leads me to the fourth insight. The Rust community acknowledges and celebrates all contributions. We do this in part by featuring Crates of the Week. This section was introduced in issue 95. Like the project updates, this section highlights crates that could be useful to Rust users. As Hojat12000 put it on Reddit, I check it out every week to see what new crates are there and which one could be useful for me. And along with the Crate of the Week itself, This Week in Rust also highlights the creator of the crate. Kanga Liu shared this on Reddit. I also had one of my crates featured on This Week in Rust, Display Utils, by submitting it myself. It was cool to see the crate get more traffic, although with 20 plus stars, it's now a bit inflated on my GitHub profile. For the record, Kanga Liu, I don't think there is anything inflated about the star rating on that repo. It shows that people found the Display Utils crate interesting and useful to them. It deserves those stars. Go ahead and put a +1 in the conference chat if you agree. Along with Crate of the Week, This Week in Rust also features a Quote of the Week. This is one of my favorite sections. There were a few early attempts to start this feature, but it really took off with the posting of this discourse thread asking for nominations. This thread is still used today, 6 years later, to nominate Quotes of the Week. And along with featuring the quote itself, we also shout out the person who nominated the quote. S. Sokolo on Reddit shared this experience. It was quite satisfying to see my name in the thanks for suggesting line on several Quotes of the Week. If you see someone say something clever, brilliant, insightful, or just funny in the Rust community, please consider nominating it for the Quote of the Week. Quotes of the Week are how we laugh together, sometimes cry together, and know that we are not alone. And this brings me to the fifth and final insight. No Rustation is alone. No matter what our level, no matter what our background, we are not alone in our interest in Rust. As Code 1985 put it on Reddit, that is always fuel to me to remember that I'm not alone who uses Rust. Even if you feel like you're the only Rustation on your team, or in your company, or in your hometown, there is an entire community out there who both shares and cares about your interest in Rust. In the past year and a half, this has become even more important. DenB92 posted on Reddit, when it comes out, I know a week has passed in quarantine. Quarantine has been hard on all of us. Among other things, it stopped in-person meetings of most Rust meetups. However, most of the meetups did not shut down completely. They moved online. Suddenly, you can go around the world and back every week through virtual meetups. I particularly enjoyed attending meetups in Washington, D.C., Dublin, Ireland, Eastern Europe, and more from my hometown in Seattle, Washington. Even in forced isolation, over the past year, I have felt more connected to the global Rustation community than ever before. When communities are online, we don't ever have to feel alone, no matter where we are. I remember experiencing this in the early days of the internet when I thought I was the only Star Wars fan in my small Midwestern town. I connected to Star Wars bulletin boards on the internet and suddenly was reading from messages from so many people who shared the same interest and passion as me. Online community became even more meaningful to me later on when, as a gay teenager at a small Catholic high school, I was able to find others online going through the same realization that I was. This may have very well saved my life, knowing that I wasn't alone in this world. Remember, the Rustation community is as mature as it is, as empathetic as it is, through the efforts of every one of you. You make this community the way it is. As I move toward concluding this talk, I hope you take this with you. This Week in Rust is a community project. It's created for and by the outstanding Rustation community. This means This Week in Rust is your project. No matter how long you've been interested in Rust, no matter what your level, no matter who you are, your contributions are welcomed and valued. It's your newsletter. It's our newsletter. And its success is because of every one of us. To subscribe to it, head on over to thisweekinrust.org. To contribute, either open a pull request on our GitHub repo at github.com/rustlang/thisweekinrust, or tweet at us at thisweekinrust on Twitter. And just before I close, I do want to make sure to call out all the previous editors of This Week in Rust, including Ember R. Links, Brian Anderson, Vikrant Chaudhary, and Flavio Ditz. Please, everyone, put 3 cheers in chat for all of them. Thank you.
And that's going to do it for RustConf 2021. Thank you all for coming. Once again, I want to give a huge thanks to all of our sponsors and all of our speakers. This conference could not happen without you. If you check the announcements channel, you'll see a link to a feedback form. Please take a moment to fill it out, and especially to give some praise to your favorite speakers. That's it. RustConf will be in person next year. I'll see y'all in 2022.